Good morning to everyone. My name is Vitor Monteiro and I'm here on behalf of Professor João Luís Afonso, General Co-Chair, and Professor Gabriel Pinto, General Co-Chair. And it is a very pleasure for us to welcome you to the second edition of the International Conference on Sustainable Energy for Smart Cities. This is the opening session, and we'll show you some details about the papers and about the program. This is a virtual conference, as you know, due to this the world situation, but we'll try to do our best. We will do our best to have the full success with this conference. So regarding the papers and the submission process, in total you have 27 papers that were submitted at the initial stage. These papers were submitted from different countries, including, for instance, Portugal, of course, Brazil, United States, Germany, United Kingdom, from different countries, as you can see. These papers were submitted from 12 distinct universities, companies, and the acceptance rate was almost 50%. This value was a requirement to have the papers indexed in the Scopus. You have 3 reviewers for each paper. It was the minimum value for each paper. You have more than 3 reviewers for some of the papers, but the minimum was 3 reviewers for each paper. So regarding the program, you will start right now with 3 papers that will be presented. We would like to highlight that you have enough time for each paper, enough time to run the video, and after that, depending of the time of each video, you have enough time for the questions and answers with interaction between the author and the audience. So you have enough time for each paper. After these 3 papers, we have a virtual coffee break, and we return again at 11 o'clock to present more 3 papers during the morning. After that, you have the break for the lunch, and you return at 13:30 to present more 3 papers. Again, a new virtual coffee break, and you return for the last 4 papers of the conference. And after that, we will have the closing session. So, again, thank you very much for your attendance. It is a pleasure to welcome you to the conference. Enjoy and pay attention to the presentations. Thank you very much.
Dear ladies and gentlemen, let me welcome you to the EAI SESC 2020 conference held in this virtual interactive setting. I'm Kristina Petrovichova, and I would like to address all of you on behalf of EAI and SESC. I would like to use this opportunity to address the Organizing Committee, the authors, and all the participants on behalf of all of us here at EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the General Chair, João Afonso, and the General Chairs Vitor Monteiro and Gabriel Pinto, together with the whole Organizing Committee, for their hard and excellent work during the conference preparation. Today, during this streaming, we would like to invite you to participate in the Q&A sessions. During each video, please write your questions about the current presentations in the chat window. After the presentation is done, the session chair will ask the selected questions to the authors of the presentation in a live conversation. Lastly, I would like to use this message to invite you to join us again at the EAI SESC 2021. Should you be interested in becoming a part of the next year conference, please do not hesitate to contact us at the email address below. Similarly, if you are interested in discussing the other possible cooperation, a conference, a workshop, or a new event altogether, please contact us at this email address as well. Thank you for your attention and enjoy the EAI SESC 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Good morning to everybody. Thank you very much for attending my presentation. I am Rodrigo Guzman from the University of Applied Science South Westphalia, located in Germany, and today I will talk about design of current controllers for three-phase voltage pulse-width modulated converters for different modulation methods. Please allow me to say some words about me. I got my bachelor degree in electrical engineering from the Santa Cruz de la Sierra Private University in Bolivia. After that, I spent like 5 years working as field service engineer in Siemens, working in 2 locations in Bolivia and Chile. I was set as a specialist for automation and drives. During my time in Siemens, I was very interested on electrical drives and power electronics, and because of that, I have decided to acquire a deeper understanding on power electronics, and I have applied for a DAD scholarship and finally came here to Germany to study a Master of Science in Electrical Engineering in the South Westphalia University of Applied Science. Currently, I am still working in the university as a scientific employee, and at the same time I am working towards my PhD in the University of Bolton. My research interests are power systems and power electronics. Which one is the outline of my talk is as follows. First, I will do a very rough introduction about where the current controller is, why the current controller is so important in applications that are related with power converters that are connected directly to the grid. Then we will talk about the details of the system modeling, which one is how we see the plant, which transfer functions we can derive from the physical plant, in our case the power converter, the coupling inductors. Then later on we will jump into the technicalities of how we can derive an appropriate proportional gain. That is, this derivation is made in a very general way, such that the methodology can be applied for different modulation methods. Then I will show you how this proportional gain looks like when we have a 2-level pulse-width modulation converter, how the gain looks when we have a 3-level MPC converter, and how the gain should be set when we use, for example, space vector modulation as modulation method for our 2-level pulse-width modulated power converter. Then I will show you some experimental results of a system designed according to the suggestions that we are doing we are giving to the proportional gain. This specific application is in StatCom and the static compensator. Finally, I will perform the conclusions. So the introduction. We have, in this the typical case that when we have a power converter that is connected to the grid, we have typically some kind of DC to AC converter that is coupled to the power grid through some coupling inductors. Generally speaking, this power converter is governed by a control system who has 2 layers. The first layer is the outer loops. For example, in the case of in the case of a synaptic power filter, that is another application of power converter connected to the grid, we can have two outer loops. One loop that is, for example, in charge of calculating the reference that the converter should inject on harmonic frequencies to compensate harmonic distortion, for example. Most of the times, this specific application, the synaptic power filter or the StatCom, for example, they come with a self-supporting DC bus, meaning that in the DC side we have just a capacitor, not any kind of power source or energy storage, for example. Means that the converter itself or the control system itself should take care that we maintain the voltage level in the DC side constant. Because of that, we need to set up a DC bus controller who is in charge just to exchange fundamental power with the grid at the fundamental frequency in order just to active power to the grid just to maintain the DC bus voltage level here constant. These outer loops, they could vary depending on the application. For example, if this were an electrical drive, that actually the same structure is applied more or less, just as in this part we have a electrical machine instead of the power grid. These two controllers will be, for example, just the speed controller, for example. Yeah. And these outer loops are changing depending on the application. But in general, we will have always an outer loop. And what is common for most of the applications that we will have always an inner current control loop. So actually, the performance of the complete system is heavily depending on the performance of this current controller. The current controller, the inner current controller, is basically receiving the reference for the outer loops, and based on the reference that he is receiving, we measure the currents that are flowing into the grid or into the machine. That doesn't matter. We calculate the error. That is passed to, for example, some kind of controller. It can be, in simple terms, can be just a proportional controller, for example. In another more advanced setups, can be a proportional integral controller, or could be even a resonant controller. After this, we have the references for the voltage that the DC to AC converter should produce in the of the output terminals, because at the end of the day, the current that we're injecting into the grid or into the machine is just driven by the voltage difference between what we have in the output terminals of the converter and what we have in the load side. And so at the end, the job of the current controller is just to produce the voltage reference that ultimately is going to be synthesized by the pulse width modulator. In the specific case of the StatCom or the synaptic power filter, we have also an extra part in the controller, which is the feed-forward controller, that is just in charge to decouple the AC dynamics from the dynamics of the power converter. And also it has the big advantage that using this feed-forward block, we can reject the disturbances theoretically perfectly, so that we can just focus on the design of this part of the current controller just with a high emphasis on reference tracking. Okay, this is the motivation. Let's jump into the current controller system design, the modeling, the design, and etc. Typical application, for example, for a two-level converter is this setup when we have the inverter that is connected to the power system through these coupling inductors. How we model this in a continuous domain is as follows. First, we have some inverter gain that is related with how big is the voltage in the DC side, and the gain that is brought by this inverter is normally, when we are working with a power converter that is working with isolated neutral, is half of the voltage magnitude to the DC side, and the transfer function of the coupling inductor when it's represented in the continuous frequency domain is, of course, 1 divided by Ls plus Air. This is typical. We need to recall that the voltages that are produced here at the output terminals of the power converter are depending of the inverter gain. For example, depending of the DC bus voltage. And we can control these voltages produced here at the output of the converter just by the duty cycle. Now, this is typical that we can control how big is going to be the voltage that is going to be produced by the inverter just by setting up the duty cycle or the modulation index. Because nowadays most of the current control is done in some kind of microprocessor, some kind of digital system. We have some delay that is approximately one sampling period of the pulse width modulation that can be represented in the continuous domain by this dead time or transport delay or time lag transfer function. And this is important to notice because the stability of the system is going to be, of the complete current control loop, is going to be heavily affected by this dead time, that is of course depending on the switching of the switching frequency of the system. With this in mind, we can look at how a typical current control loop looks like. We have the reference, for example, could be here. This is the output. We sampled reference and output current at precise instance during the complete switching frequency period, and we try to actually to measure the current without ripple just by measuring the current when we have a zero vector applied to the three-phase system. We calculate the error. This error is passed to the current controller that most of the times is discrete. As I mentioned before, we had this feed-forward part when we are measuring actually what is the, in the case of the grid voltage connected power converter, we measure which is the voltage that we measure the voltage at the point we are sampling the currents. We fed this information again into the modulator. The idea is that as the voltage is entering into the system here as positive and here as negative, because the current at the end, as I said before, is just defined by the voltage difference between what the inverter is producing, what the grid is having, and the difference between these voltages and the transfer function of the coupling inductor is going to define the current that is flowing. So when we have here a plus and here a minus, definitely what we are doing is that we are canceling this distortion that it represents for us the voltages of the grid. All this information here, that is the M, the duty cycle, is passed to the discrete pulse width modulator. As I said, we have one delay of one pulse width modulation sampling period, because we need always an amount of time, between we sample the current and we calculate the appropriate duty cycle after the error is calculated to fit the new modulation index. And this is represented by this delay block here, or by this delay block that has this transfer function. And finally, of course, we have the inverter gain as it's depicted here, and this represents my complete closed loop system. Working with this kind of transport delays is a little bit difficult because this transfer function is infinitesimal, in theory meaning that it has infinite poles, and of course that makes the design of a certain controller very difficult. So some authors, for example, Buso, or they try to approximate this transfer function just by path approximations, such that they reduce the complexity of the plan, going from infinitesimal transfer function just to finite transfer functions. Even some this is, for example, a path approximation of first order. When the frequency of the modulation index that we are fitting here is small enough in comparison with the switching frequency, this approximation makes sense. But in many applications, actually, this is not true. So, of course, for the design of the current controller, it will be much better just to consider the complete transfer function with the transport delay block. Even some authors simplify this even more just by expressing just one first order system as approximation for this dead time. Of course, these two will lead to some errors and deviations on the behavior that we're expecting from the current controller, and it's much better to design the current controller having on mind the complete transfer function, including the transport delay. So with this on mind, we can take a look. This is also our converter with the coupling inductors. When we portray this to transfer functions, we have this the model that I have shown you before, but just 3 times, one for each phase. And if we consider just the output to reference and we try to look for the looped transfer function, when we consider just a proportional current controller, we will get that the open loop transfer function is equal to the proportional gain Kp. Following this path, the proportional gain Kp. You have here the model of the inverter, that is just the gain of the inverter, times this transport delay that is produced by the digital implementation of the pulse width modulator. We encounter the transfer function of the coupling inductor. This is for us the open loop transfer function, and this is our starting point for the controller design. Actually, all this derivation was the derivation that we will show now has been already done by Holmes in 2009. And what is the novelty that we are just doing is just taking the procedure that Holmes did, and in the past for 2-level pulse width modulator converters, we are just generalizing what was his work to other 2 types of modulation methods. So how we start is as follows. We start with we take the open loop transfer function. We say, okay, we want to calculate the phase of this, the phase of the complete open loop system. That means that we should consider, okay, when we are talking in phase, and we have here a product of transfer functions. In talking about phases, this means that we have a sum. We should calculate the phase contribution of the first part of the open loop transfer function plus the contribution of the dead time transfer function plus the contribution of the coupling inductor transfer function. Normally we can disregard this resistor because normally it's very small, and what is the most important for the dynamics is just the magnitude of the coupling inductor. So the phase that is produced by some constant gains is 0. The phase that is produced by a dead time, when we look at frequencies that are high meaning we are in the range of half of the switching period, we will see that the phase that this kind of element is introducing is actually directly proportional to the frequency. And in the worst of cases, this transfer function here will introduce always a lag of minus 90 degrees of p divided by half. If we recall that the phase margin definition is how many degrees we are far away from or above the minus 180 degrees point, we can actually say, okay, for a respective phase margin, that a decided phase margin that is defined like this, which one is going to be the frequency or the crossover frequency that is going to produce or is going to, or which one is the crossover frequency of the system who will lead ultimately to acquire this phase margin. So basically we replace this expression here, that is the definition of the phase margin over what is the phase contribution of our complete transfer function. We have it here. 0 is disregarded, we have just these 2 terms, and finally we end up that the crossover frequency of the system for our the phase margin that can be defined by design is equal to this expression. So for instance, if we say that we want to have a phase margin of 30 degrees, that is actually, we setting the phase margin to 30 degrees, we say we are trying to have a current controller that is very, very fast, that is stable, of course. Actually, this is for a good control design, this is the minimum phase margin that we can choose. So the minimum phase margin that we can choose we are being stable, but at the same time we are also very fast. Recalling that 30 degrees is p divided by 6, we replace this in this expression, and we end up that the recommended crossover frequency of the system is this one. And if you recall that if you use double update when in the modulation, meaning that we are always sampling at the both zero vectors applied over a switching period, meaning that the delay of the produced by the modulation process is just half of the switching period, we end up that the suggested crossover frequency for a fast current controller is directly proportional to 2 pi the switching frequency divided by 3. And this is our recommendation for crossover frequency. So the question is, okay, we have now which one is our desired crossover frequency that we want to have depending on the switching frequency of the power converter. Now the big question is how we manage to have an open loop transfer function with this crossover frequency. Then we need to go back again to instead of looking at the phase response of the system, now we look at the magnitude response of the system, meaning that the magnitude of the system in dBs, of the open loop in dBs, is going to be equal to the contributions to the magnitude of all of the elements that are inside. First of all, we have some kind of constant gain, that is where all these three are included. I have just split the inductor influence from the previous transfer function. I have just split this transfer function when the resistor is disregarded, was just pass it here. We have this contribution, and then we have the contribution, of course, of the transfer of the delay element, of the dead time element, and then we have the contribution of an integrator. The dead time in phase is not, or in magnitude, is not introducing any contribution, so the complete magnitude of the open loop transfer function is going to be defined by these terms. If we recall that at the crossover frequency of the open loop transfer function, the magnitude is 0 dBs, then we have the contribution of magnitude of the gains minus the contribution of the integrator. The contribution of the integrator in the case of the magnitude is always a negative, is always ramped down. So we have the contribution of a simple integrator as always minus 20 dBs, that is directly proportional to the logarithms of the frequency. If we want to know which is going to be the Kp that's going to be produce the crossover frequency that we have selected in our previous slide, I can solve this equation that finally leads to the suggested Kp to achieve a crossover frequency that is equal to the crossover frequency itself times the inductive divided by the gain of the inverter. We replace the crossover frequency from the last slide, and finally the Kp that is suggested to have a very fast and stable current controller is equal or is proportional to the switching frequency, is proportional to the coupling inductor, and is eventually proportional to the gain of the inverter. This is the general form that we need to have in mind. In the case of a two-level converter, pulse width modulator, this is very easy because the inverter gain is always the DC link divided by 2. So we just replace this in the former expression, and the recommended Kp for pulse width modulation will have this expression. So all with the Kp of the current controller is just influenced by all the parameter designs of our power inverter. If we talk about a 3-level converter, MPC for example, Reddy Jansgani in his book in 2010, he ended up that the average model of these two kind of converters is exactly the same. So the same of these gains is the one that are the gains that are recommended for these two kind of power converters. One of the other very small contributions of this paper is to the question to, okay, how to set the gain when we are using space vector modulation. And this has been derived just in some very basic premise. And is that, okay, we know that when we are using just pulse width modulation, normally pulse width modulation, we know that the amplitude of a particular voltage vector that we can produce in our inverter is just limited in amplitude by half of the DC bus voltage. In the case of the space vector modulation, we are always restricted to have the amplitude of our voltage space vector just within the hexagon in this case. With this limitation, we know, okay, we can say that the maximum amplitude that a particular voltage vector can achieve using space vector modulation is the DC link voltage divided by a square of 3. There is some small improvement here, 15% in the amplitude of the voltage vector that we can produce by using space vector modulation. So just by inspection, I can conclude that the in-gain inverter, in the case of when we are using space vector modulation, is the DC bus voltage divided by a square of 3 instead of this one. That will lead us to the recommended proportional gain when we are using space vector modulation, having this form. Okay, so far so good. Let's jump into the experimental verification. We have small prototype in our lab that is that has exactly this form. It's just three-phase converter with just capacitors in the DC side that is connected to the grid to some coupling inductors, and the picture looks like this. We have the DC bus here that is just capacitors. We are working always with 750 volts of voltage in this DC side. The complete capacitance is 8 millifarad. Then we have the three-phase converter. We are using silicon carbide MOSFETs with silicon carbide Schottky diodes, anti-parallel diodes. Then we have here the coupling inductors, 100 microhenries coupling inductors that have amorphous material as a core for the magnetic core. This is the fan that is just cooling the cooling, of course, the semiconductors. So that the heatsink is not so clear here, but all these MOSFETs are sitting here in the heatsink. Then we have a ripple filter, and the ripple filter is just an RC circuit that is on the output of the three-phase converter, just to try to catch the switching ripple that it should not be going to the grid. And this is the values of the ripple filter. These are the protection fuses, and here we are connected to a distribution transformer of 12 kVA, and the complete power system, the external power system, has a voltage of 400 volts line to line, 50 hertz. How we have generated the reference currents for this experiment is that if we recall the instantaneous power theory, the active power has this expression when the voltages are the voltages that are generated by the grid, or they are related with the grid, and the currents are related with the currents that the converter is injecting. So we have these expressions for the active power, and we have these expressions for the reactive power. If we decided to inject a particular amount of reactive power and active power to the grid, the references for the converter can be calculated based on these in this formula, and this is the how we are setting the reference for the experiments. So in the experiment, we have used our grid tie connected converters on the STATCOM. I forgot to say that the controller that we are using that is implementing is executing all the control in digital form is a Texas Instrument Delfino microcontroller. In this case, the STATCOM had a self-supporting DC bus, so in order to maintain its DC bus constant to 750 volts, the controller was always demanding 600 watts in order to compensate the internal losses of the converter. What we have set manually is the reference for the reactive power to 12 kVA reactive. These are the currents that we have measured in our experiment. So you can see here that there are three-phase currents. You can see the ripple here because of the switching process. The ripple here is magnified a little bit to check the ripple in the three phases. The complete ripple is 20 amps peak to peak, I think, because of course we are working with a coupling inductor. This is a little bit small, 100 microhenry, so you can expect a very big ripple there. And important to notice is that each of the measured RMS currents that the inverter is injecting is almost 70 amps, meaning that we are when you multiply 17 amps times 230 volts, that is the line to neutral voltage times 3, we get something like 11.7 kilovolt ampere, meaning that okay, our grid power converter is following very closely the reference that we set for the reactive power. And of course, in this case, our controller, or the current controller that was implemented in the board, in the microcontroller, was following the gains that we have shown in the previous slides. So finally, to conclude, because we are running out of time, an analytical formula to calculate the proportional gain for a current controller has been shown for a pulse width modulated converter when we are talking about 3 different modulation methods. The idea of the formula is always to guarantee a proportional gain for the inner current control loop that is stable, and at the same time it's very fast because the phase margin is just 30 degrees. And some further application of this formula can be, for example, it can be used for an adaptive current controller. In the case that when we have a nonlinear coupling inductivity or coupling inductor, when the Li curve is not linear in some regions, but is continuously decaying, you can adapt the proportional gain based on this characteristic of the shock just by a lookup table that is relating how much current is decided to be produced and which one is the inductivity value for the current that we want to produce. So with that, I want to conclude my presentation, and I will be looking forward to interact with you in the question and answer session. Thank you very much. Good morning to everybody. Thank you very much for attending my presentation. I am Rodrigo Guzmán Iturra from the University of Applied Science, Südwestphalia, located in Germany. Today I want to talk about limits of harmonic power recovery by power quality conditioners in 3-phase, 3-wire systems under non-sinusoidal conditions. The outline of my talk is as follows. First, I will talk about the motivation that is power quality problems and harmonics. Basically, I will focus more on voltage harmonic distortion. Then I will state some power definitions that I have used in my work. Later on, I will show you 2 formulas that we have derived to calculate the maximum amount of harmonic active power that a particular power quality conditioner or shunt active power filter can recover or can transform from the power grid. Then later on we will see some simulation that is validating the formulas that we have derived, and finally I will perform the conclusions. The complete idea of the presentation is that most of the times which one is the energy savings that a particular shunt active power filter can achieve, most of the times are inflated by some of the vendors, because what they try to do is they try to inflate these energy savings in order to sell a particular solution. But actually the energy savings, the real energy savings are much smaller, definitely. And the idea of this complete work is just to provide a formula that is which result is real estimation or particular estimation of the maximum amount of energy saving that can be achieved. So we jump into the technicalities. The motivation for our work. What is power quality? Power quality for for us, when we are talking about typical distribution systems, 3-phase distribution systems, we have of course some kind of utility that is delivering power. Probably we will have also distribution transformer, because the connection to the utility is mostly in medium voltage in some range of 20-30 kilovolts, and we need to decrease that voltage to work in the range of 400 volts line to line, for example. And because of that, we will have some kind of distribution transformer just for adapting the voltage. And finally, the different loads that a particular industrial facility will have will be connected to the transformer, and this point where all the loads are connected in parallel is known as the point of common coupling. Normally what we expect is that the voltages at the point of common coupling, the voltage that is supplied all the load, should be as sinusoidal as possible. Sinusoidal meaning with a particular magnitude of 230 volts line to neutral when we are speaking about Europe, and a normal frequency of 50 Hertz. That is what we consider power quality, or a grid with a very high power quality. When these voltages at the point of common coupling, they have a sinusoidal feature. Most of the times, or in the past at least, when we have just linear loads, for example, typical induction motors or just light bulbs that are linear, meaning that they always draw the currents with the same frequency as the voltages that are supplying a particular load, we will have the case that the voltage is going to be very sinusoidal. And this is not, at least in the past, with typical loads, linear loads, the quality of degradation of power quality was not a big problem in industrial facilities. However, nowadays, many of the conventional loads have been replaced by some kind of power electronics driven loads, because in order to achieve some high controllability or flexibility in the industrial processes, many of the conventional linear loads have been replaced by, for example, they have replaced induction motors just by variable frequency drives. They have replaced the light bulbs just by LED lighting, that they are more efficient. And for example, they have been other kind of particular machines that we didn't have in the past, like for example robots. The problem is that all these kind of loads that are driven by some kind of electronics, what they are doing is that they are producing voltage distortion in the grid. And what it should be, in theory, a very nice sinusoidal voltage becomes very distorted because of the very presence of these loads. And the very interesting thing is actually the loads more affected by the distortion that is produced is actually this kind of loads. So they are producing the distortion, and they are the most sensitive to this kind of distortions. When we have this nonlinear loads, what is happening is that utility is transferring some amount of power to the loads. But because of the loads, they have some kind of nonlinear nature. What they are doing is they are returning back part of the energy that they are absorbed. They are returning this energy over the time back, and actually this kind of power at the end of the day is dissipated in the resistive parts of the transformer, for example, or in the resistive part of the transmission lines, leading to energy waste. And of course, that reduces the efficiency of the complete distribution system, and this is not very nice. A way how to solve this problem is we can install some kind of Schonactive power filter. And how a Schonactive power filter can be understood is like a controllable current source. So basically, what the Schonactive power filter is doing is injecting currents into the system when it's connected in parallel to the loads. It's injecting currents such that the harmonic currents produced by the nonlinear loads are cancelled completely. And when we turn on, for example, here we're turning on the Schonactive power filter at 15 seconds, what we are doing is that the complete voltage distortion is reduced, and we have once again sinusoidal voltages. So basically, Schonactive power filter or a power quality conditioner, what it's doing is that is reducing the voltage distortion. Because the voltage distortion is reduced, of course, the loads are going to be protected, because they are not going to be subject to some kind of very high rapid changes in the voltage that is supplying these loads. The other part is also interesting, is that the energy or the power that is returned back by the nonlinear load is harmonic power, instead of being dissipated in the transformer or in the resistive part of the distribution lines. Is part of this power is absorbed and processed by this inactive power filter. So up to here everything is fine and everything is good. What you need to be stated is that as an active power filter was mostly meant to provide this protective feature to the loads, because at the end of the day, what is the main objective is just to compensate for the harmonic distortion, meaning producing a very nice sinusoidal voltage in order to protect the loads. This feature of processing or transforming the power that is injected back, reflected backwards by the loads, the inactive power filter is doing. But the problem, as I said at the beginning, is that this transformation of the power that basically leads to energy savings, because when we are processing the power that is injected by the nonlinear load that was causing low efficiency before, when we are capturing this and transforming this to produce again useful power, we are producing energy savings. The problem is that, of course, many of the vendors of power quality solutions are inflating how big the energy savings can be. Some of them, they claim energy savings in the range of 20 to 30%, but in reality this is much lower. And what we did in our work was to formulate, to investigate, and finally we end up with an equation that is telling to the end user basically under this and this grid conditions, this is going to be the maximum amount of harmonic power or the energy savings that you can have when you install a particular inactive power filter for power quality condition. Okay, with this in mind, we go to some power definitions. We have taken a three-phase system. We have considered that the complete transformer can be represented by this equivalent impedance, just a resistive part of the transformer, and some kind of inductivity that is related with the leakage inductance of the transformer. The utility grid impedance also can be included in this equivalent circuit, but the impedance is mostly dominated by the impedance of the transformer. We have the voltage that the utility is supplying. This voltage could have also, we'll have some fundamental part, some 50 Hertz voltage, that is the main part, but could have also some harmonics present on it, just background distortion. Then we have the point of common coupling. At the point of common coupling, we have linear loads connected. So, for example, loads of the nature resistive inductive, like typical induction motors, and we can have also some nonlinear loads, like the frequency converters or the robots that we saw in the last slides. If we look at the voltages and currents at the point of common coupling, if we have nonlinear loads connected to the system, then the voltages at the point of common coupling, they will have some component at the fundamental frequency in 50 Hertz plus some harmonic components. And this can be, of course, represented by a Fourier series. In case of the same system, the currents that are drawn by from the power system, they will have exactly the same frequency components of the voltages at the point of common coupling. That can be expressed in Fourier series also by this expression. When we talk about the effective value or the root mean square value of the voltages of currents in presence of harmonics, we need to recall the definitions of Buchholz that were once more stated by Emmanuel in his book of 2011, where the RMS value of the voltages in presence of harmonics is related by the square root of the sum of the square of all the components in the voltage or current. Once again, we need to recall what is the total harmonic distortion. The total harmonic distortion is just the relationship, the ratio between the harmonic content of a particular quantity, for example, the harmonic content of the voltage divided by the fundamental component of the voltage. That is also, or it can be also equal to the square root of the RMS that we are measuring at the point of common coupling divided by the fundamental voltage, everything squared minus 1. We can define the total harmonic distortion either in voltage or either in current. And actually there is European limits for European, or there is limits depending of the normative that are defining the maximum amount of THD that a particular industrial facility can have either in THD or in THDI. Okay, if we look at the apparent power resolution for non-sinusoidal conditions, the apparent power, the general term in a three-phase system is 3 times the RMS voltage times the RMS current. But because also the current and the voltage, as we saw here, they have a fundamental and harmonic part, we need to consider all this in the apparent power resolution. If we square this equation, we will have the following equation, that is 9 times the effective voltage square, that is just the sum of the fundamental voltage square plus the harmonic content of the voltage square, times the current, that is it has also some component, that is fundamental current square plus the harmonic content square. We can work this further, and at the end of the day, what we will have is that the apparent power under non-sinusoidal conditions will have 4 components. The first component is the classical apparent power, the fundamental frequency, that is just the voltage of the fundamental times the current at the fundamental, that multiplied by 3 in the case of a 3-phase system. But then we will have other 2 distortion powers. The first one, that is the largest, is the total current distortion power, that is this one here, that is just the product of the voltage of the fundamental frequency times the magnitude of the harmonic content of the currents. This one is the largest of these power distortion power apparent power distortion powers. Then we have the total voltage distortion power, that is just the voltage of the harmonic content of the voltage times the fundamental current. And then we will have the harmonic apparent power, that is just the interaction of harmonic voltages and currents This one can be actually analyzed further and can be divided in 2. One is the harmonic active power, that is actually the one that is producing, or is the amount of power that is returned back by the power loads, and actually this is the only amount of power that can be processed or recovered later by active power filters in order to produce energy savings. And the second part is just a distortion harmonic active power, that is just interaction of harmonic voltage, this is the result of the interaction of harmonic voltages and currents at different currents. This is just producing most of the time just reactive power. We jump up a little bit in the technicalities of the total harmonic power, that is just what is the average power, the instantaneous power, when we talk about harmonic voltages and currents, is this expression with this averaging over one grid period is going to have this average value. This harmonic power here is the only one who has average real power, because all the rest is just oscillating. The rest of the powers are just oscillating and just producing reactive power. Okay, if we could actually express each of the distortion powers as functions of the THDU and THDI, and this is just very easy to do. We just take the definition, for example, for the current distortion power, we divide that by the apparent, we multiply and divide that for the fundamental apparent power, who has this expression, and then you will see that these two will cancel, for example, the 3 will cancel, and we can see that the current distortion power is going to be equal to the fundamental apparent power multiplied by the ratio of the harmonic content divided by the fundamental current. Actually, the current distortion power is going to be just proportional to the THDI times the fundamental apparent power. The voltage distortion power, following the same procedure, is going to be just proportional to the THD in the voltage times the fundamental apparent power. And we can do the same, for example, also for the harmonic apparent power. At the end of the day, the harmonic apparent power is going to be just proportional to the fundamental apparent power times the THDU times the THDI. And we can also represent the complete total apparent power that had this expression before. We can replace just this 1, 2, 3 in the equation that we saw at the beginning. We can replace that, and actually we can express the complete total apparent power as function of the THDU. These are mostly the expressions that we will use to calculate which one is the energy potential that the Schoen active power filter can achieve. The determination of the limits of the harmonic power of energy savings. When we look at this equation here, we know that the harmonic active power is going to be related with the harmonic apparent power. And actually, the harmonic apparent power is related with the fundamental apparent power just by the product of the THDs. That is coming from this equation. Yeah? Meaning that, for example, actually, the harmonic active power is going to be always smaller than the apparent apparent power from the harmonic frequencies, meaning that the upper bound for the harmonic active power is going to be always the harmonic apparent power. So we are going to say always that any kind of energy saving potential that a particular Schoen active power filter can achieve just by processing harmonic active power is going to be bounded by the apparent harmonic active power. That means, for example, that if a particular facility has an 8% distortion and 8% harmonic distortion in voltage, 60% distortion in current, the maximum amount of energy savings that any kind of power quality conditioner, for example, a filter can achieve is just 5%. Not more. This relationship between the harmonic active power and the fundamental power sometimes is a little bit difficult, because this fundamental power is not all the times available. What is available most of the time is the complete total apparent power. That is something that we can measure just by measuring the true RMS of the voltages and currents. If this is the case, we can relate the apparent harmonic power to the complete total apparent power just by this relationship, and at the end we will see that the ratio of these two powers is equal to this expression. So again, if you consider that a particular industrial facility has an 8% voltage distortion and a 60% current distortion, then the maximum amount of energy savings that can be achieved related with the total apparent power is just 4.1%, not more. So these two formulas are the ones that are going to say exactly how much harmonic power we can recover, which one is the really energy potential saving that it can be achieved. And this is of course far away from the 20-30% that some of the vendors promise. Okay, simulation validation. We have performed a simulation in order to validate our two formulas. We have considered a distribution system who has a distribution transformer of 2 MVAs, impedance 5%. We had in the load side 400 volts. We have considered a nonlinear load, a passive rectifier with smoothing capacitors with a power of 700 kilowatts. There have been another kind of loads, other inductive resistive loads that had a complete rating of 700 kilowatts and demand of 100 kVA as fundamental power. We have also considered that there was some harmonic voltage distortion background here, that is at the fifth and seventh harmonics. And in all this study, we have assumed that the impedance was completely dominated by the transformer. Okay, when we have simulated the system, we have measured the THDU, that was around 7.9%. We have measured the currents at the point of the currents drawn by the power system. We have measured that the total harmonic distortion in current was 26%, and we have done all our studies in according to this European norm. So you can take the voltages and the currents of the three phases, and you can do some Fourier analysis. And for each of the harmonic frequencies, for example, the fundamental, the fifth, the 7th, the 11th, the 13th, and so on, you can calculate the components and the respective phase angles. And with this information, we can calculate each of the components of the apparent power resolution, leading to the following expressions. Here we need to highlight the following. What is the most important is that the harmonic active power that is generated by the nonlinear loads is around 3.7 kilowatts here, and that the harmonic apparent power is around 28 kilowatts. And these are the two expressions that we need to look if our formulas are passing or are in accordance with these two. The fundamental power that is drawn from the grid is around 1.3 megawatts, and the simulation says that the complete apparent power, including harmonics, is 1.4 megawatts, more or less. No. Okay, so let's check the formulas. The first formula that we set was that the upper bound of the fundamental of the harmonic active power related with the fundamental is just the harmonic apparent power that it was just proportional to the THDU, THDE, and we said that the upper bound was calculated with these two values measured in the simulation is 28 kilowatts, calculated here. That is actually very nice in according with what we measured in the simulation, so that means that this formula is correct. We have actually test our second formula that is related with the total apparent power. Here also related with THDU, THDI, and we see also that the bound of the harmonic active power, that is the apparent harmonic active power, is also very close to what we measured in the simulation, so this formula is also valid. Meaning that if we install a harmonic active power filter in this facility, the maximum amount of harmonic active power that we can process and return back to the grid is going to be maximum 2%, and this is the realistic value. Okay, please allow me to conclude my presentation. Two formulas were provided to calculate the upper bound of energy savings that can be achieved by some kind of power quality conditioner when it is processing harmonic active power. And the realistic value, actually the real value of the harmonic active power that can be calculated is going to be somewhere between 10 to 50% of the upper bound that we have suggested. And we suggest to use this formula to calculate the amount of harmonic active power that can be saved by a particular power quality conditioner. I want to thank you for your attention, and we would like to, I will be looking forward to interact with you in the Q&A session later on. Thank you very much.
Hello everyone, my name is Sergio Coelho and I'm a researcher at University of Minho, Portugal. So, today I'm going to present a paper called Comparative Analysis and Validation of Different Modulation Strategies for an Isolated DC-DC Dual Active Bridge Converter. Starting from the beginning, a dual active bridge converter, or more commonly known as DAB converter, was introduced in 1991 by Rick D. Donker in a scientific article called A Three-Phased, Soft-Switched, High-Power Density DC-DC Converter for High-Power Applications. As it is possible to observe, the architecture of this power converter is quite simple, in which two full bridges are connected by a high-frequency transformer, a configuration that can provide a large number of advantages to the power system. Besides galvanic isolation and bidirectional power flow, there is the possibility of including more degrees of freedom in the control algorithms. Moreover, since a DAB converter operates in a high-frequency regime, its power density is necessarily higher and the passive components that constitute this topology, that is, the transformer and the leakage inductance, have less volume and weight. In the early years after its invention, considering that available technology was far from what it is today, this topology was mainly applied in medium or high power applications. However, the latest trends in the field of power electronics allow the employment of the DAB converter in the interface of energy storage systems, in solid-state transformers, in electric vehicle battery chargers, in power electronic traction transformers, and, more recently, in medium or low voltage DC or hybrid power grids. As expected, the efficiency of any power electronic system must be as high as possible. And, to achieve this goal, different strategies can be adopted. In this specific case, to further increase the efficiency of the isolated DC-DC converter, new topologies derived from the DAB have been developed throughout the past few years. In this sense, it is possible to highlight the three-level DAB converter with 5 control degrees of freedom, the neutral point clamped DAB converter, the multi-level DC-DC DAB converter utilizing an LCL filter at the transformer side, and a dual bridge series resonant converter. On the other hand, the adoption of the correct modulation technique also contributes to increase the efficiency values presented by the power converter. In a DAB topology, considering the value of the operating parameters, certain control algorithms are considered more suitable than others. The direct consequence of this choice may result in the mitigation of peak currents in the semiconductors, in the reduction of the reactive power and circulating currents, in the rectification of possible issues related to the transformer saturation, in the expansion of the zero voltage switching operating range, and, at last, in the implementation of soft switching throughout the entire range of the DAB converter. Increasing efficiency of a power electronic system is synonym of reducing the total losses of any converter topology. In this sense, the total losses in a DAB converter are the result of the sum of the conduction losses, the switching losses, the transformer losses, and the leakage inductance losses. Once again, it is necessary to emphasize how important it is to adopt the correct modulation technique in a DAB converter. Thus, the most frequently employed control algorithms to regulate the direction and value of transferred power are the T-cycle modulation and the phase shift technique, in which the single phase shift, dual phase shift, extended phase shift, and triple phase shift variants stands out. On the other hand, as in most cases, the efficiency presented by a given modulation technique is associated with its implementation difficulty, being necessary to assess if the cost justifies the obtained benefits. In this regard, such a context gave rise to the work developed in this paper, comparative analysis of different modulation techniques that can be applied to a DAB converter, validating and analyzing its performance with the realization of computational simulations. Besides comparing the 4 phase shift techniques, that is, single phase shift, dual phase shift, extended phase shift, and triple phase shift, this work also verifies the operation of this topology when operating as a single active bridge converter, that is, when only one full bridge is switching while the other adopts a passive behavior. As mentioned, a DAP converter is an isolated bidirectional DC-DC converter with a simple architecture, in which two full bridges are connected by a high-frequency transformer. Given a particular application case, the transformation ratio of the transformer will have the necessary value to regulate the voltage in the primary and secondary DC links, represented in red and blue accordingly. As it is obvious, two full bridges represent the existence of 8 power semiconductors. These can be of various types, like IGBT, SiC, GaN, etc. But to increase the power density of the converter, the switching frequency of these components must be as well as high as possible. Consequently, the volume and weight of the high-frequency transformer and leakage inductance will decrease. The leakage inductance, in turn, is considered a vital component for all the modulation techniques. Besides being responsible for limiting current variations in the high-frequency transformer, the voltage drop in this component will cause a small phase lag between the voltage waveforms on each side of the transformer. The adoption of the correct modulation strategy for the DAP converter will be translated into a great number of advantages in terms of energy efficiency. Thereby, in the first instance, it is crucial to define simulation parameters, so that, consequently, each modulation technique can be analyzed and discussed in greater detail. So, in this table, the values assigned to the parameters of the DAP converter are presented, highlighting among them the value of the switching frequency, which is quite high in order to increase the power density of the DAP converter, and the transformation ratio of the high-frequency transformer. The value of 2 for 1 for this parameter allows the nominal voltage on the primary side to be 400 volts and on the secondary side to be 200 volts. However, it is vital that these values and corresponding waveforms must be controlled using appropriate modulation techniques, which will be presented and compared on the following slides. Lastly, it is important to refer that, although one of the main characteristics of the DAB is energy bidirectionality, in this work, for the sake of simplicity, only the results in which the power flows from the primary to the secondary side of the converter will be presented. These were obtained with software PSIM from PowerSim. As mentioned in the introduction of this presentation, this work is focused on the comparison of different modulation techniques that can be applied to a DAB, an isolated DC-DC converter. Thus, on the following slides, 5 modulation techniques will be analyzed, observing the voltage and current waveforms at the terminals of the high-frequency transformer and the triggering gate signals applied to the 8 semiconductors. In this sense, the first applied control technique was the duty cycle modulation. In this situation, according to the direction of the transferred power, the converter operates as a single active bridge converter, enabling switching on one of the full bridges and assigning a passive behavior to the other. Given these operating conditions, it will be the semiconductor's freewheeling die to provide a path for the current. When the power flows from the primary to the secondary side, semiconductors S1, S2, S3, and S4 are switching, while the freewheeling dies of S5, S6, S7, and S8 provides the path for the current. The adoption of this modulation technique is considered quite simple, provides great robustness to the power converter, and, most importantly, reduces the switching losses. So, in order to regulate the voltage on the secondary DC link, a PI control technique was applied. A voltage reference of 200 volts was previously defined, and the output of the control will act directly on the duty cycle value of the semiconductors S1 and S3. The triggering gate signals of the semiconductors S1 and S3 can be observed in the first figure, and, as expected, the duty cycle of these signals is the output of the implemented PI control. Needless to say that the gate signals of S2 and S4 are complementary to these ones. In all the modulation techniques that will be presented in this work, it is vital to monitor the voltage and current waveforms in the high-frequency transformer. Analyzing the voltage on the secondary side of the transformer, it is verified that it has a maximum value very close to 200 volts, that is, the pre-established reference for the voltage on the secondary DC link, thus proving the veracity of the applied control algorithm. Now analyzing the current waveforms in the high-frequency transformer, it is possible to observe that, although these currents present correspondingly peaks of 17.51 and 35.02 amperes, its mean value is null. In addition, the primary current always takes half the instantaneous value of the secondary current, proving once again the veracity of the control algorithm and that the transformation ratio is indeed 2 for 1. On the other hand, it is possible to observe a small gap between these waveforms. which, as explained, is a result of the voltage drop in the leakage inductance. The lower its value, the lower the voltage drop, the lower the phase lag, and the current peaks in the high frequency transformer. As will happen in the phase shift modulation techniques, a resistive load was connected in parallel with the secondary DC link of the DAB converter. Its value is 11.11 ohms, and for the power to be 3.6 kilowatts, the current at this point of the circuit must be around 18 amperes. Given these circumstances, in the last figure, it is shown the waveform of the current on the resistance load, presenting a mean value of 17.255 amperes, just below the pre-established value. The phase shift modulation is the control technique that is frequently applied to regulate the power direction and value in the DAB converter. In general, comparing to the duty cycle modulation, the phase shift provides a large number of advantages, all of them related to the efficiency of the DC-DC converter. As stated, there are 4 variants of this modulation technique: single phase shift, the dual phase shift, the extended phase shift, and the triple phase shift. For any of them, regardless of the power direction, each semiconductor is always switching with a fixed duty cycle of 50%. However, it is the value of the phase lag between the voltage waveforms at the terminals of the high frequency transformer that will determine the direction and the value of the transferred power to and from each side of the DAB converter. This phenomenon only occurs due to the existence of the leakage inductance. When it's generated a voltage drop in this component, a certain current will flow through it, and, depending whether the phase lag is considered positive or negative, the direction of this current will change, as well as the power transferred to and from each side of the DAB converter. In other words, if the primary voltage waveform in the high frequency transformer is in advance of the voltage waveform on the secondary side, the power will flow from the primary to the secondary side of the DAB converter. This situation is seen in this figure, where a positive phase lag value is presented. However, if the opposite happens, that is, if the secondary voltage waveform in the transformer is in advance of the one existent on the primary side, the energy will flow from the secondary side to the primary side of the DAB converter. The single phase shift modulation, among the 4 variants presented in this work, is considered the simplest and with low implementation difficulty. It is the most frequently applied control technique, since the obtained results are considered quite good from the efficiency point of view. However, the great limitation of this technique is the existence of only one degree of freedom, that is, the only variable that can be controlled is the phase angle between the 2 full bridges, called outer phase angle or D0. Since only one degree of freedom is considered, the triggering gate signals of the semiconductors S3 and S7 are 180 degrees phase shifted from the ones existent in the semiconductors S1 and S5 correspondingly. For this case, the value of D0 will be generated using a PI control algorithm, resulting from the comparison between the reference of 200 volts and the voltage value measured on the secondary DC link. As it is possible to observe in the middle image, this value of D0 is applied to the power semiconductor S3, having a value of 2.88 degrees. The existence of only one degree of freedom results in the generation of voltage waveforms with 2 voltage levels at the terminals of the high frequency transformer. As previously explained, the power flows from the primary side to the secondary side of the DAB converter, since the primary voltage waveform of the high frequency transformer is in advance of the secondary one. This situation is presented with great detail in the second image. Additionally, existing only one degree of freedom, the implementation difficulty of this modulation technique tends to be lower. However, this fact can be quite limiting, since in times of non-correspondence in the voltage levels on each side of the DAB converter, the total losses tend to be higher, with higher reactive power values, current peaks, and circulating currents. On the other hand, observing the third image, it is easily seen that the primary and secondary current waveforms in the high frequency transformer present null mean value and are in phase with the voltage waveforms. Moreover, the current peak values are considered low, which proves the semiconductor stress is also low. The last image shows the voltage and current waveforms in the secondary DC link. As it can be seen, in steady state, the voltage assumes an average value of 199.03 volts, while the current is at 17.915 amperes. Thus, the active power in the load has an approximate value of 3.566 kilowatts. a value considered very close to the desired one, which is 3.6 kilowatts. The dual phase shift is commonly referred as a modulation technique that provides greater efficiency to the DAB converter in medium-low power applications, since the value of reactive power, circulating currents, and current peaks will be reduced. These advantages are obtained with the inclusion of a new degree of freedom, called inner phase angle or D1, applied between the legs of the first full bridge. On the other hand, as it is possible to observe in the last figure, the triggering gate signal applied to the semiconductor S7 is considered the sum of D0 and D1 in relation to the gate voltage of the semiconductor S1. The inclusion of a new degree of freedom will generate a 3-level voltage waveform at the terminals of the high-frequency transformer. However, if the value of D0 is obtained with the PI control algorithm, the value of D1 is with the aid of the equations 1 and 2. These equations will allow to vary dynamically the value of D1 according to the relation between the primary and secondary voltages of the DAB converter. In this sense, the value of D1 is as high as the value of the calculated ratio. As for the single phase shift, and by observing the first image, the primary voltage waveform is in advance of the secondary one at the terminals of the high-frequency transformer. This situation proves that the power flows from the primary to the secondary side of the DAB converter. On the other hand, by observing the current waveforms in the transformer, it is possible to conclude that, as expected, its mean value is null. Although the current peaks are higher than in single-phase shift modulation, the stress in the power semiconductors will be much lower. This statement is justified due to the existence of moments where the instantaneous value of the current is almost null. As for the other 4 modulation techniques, it is necessary to monitor and regulate the voltage on the secondary DC link. In steady state, it is essential that its value is as close as possible to the 200 volt reference. The last figure shows the regulation of the secondary DC link voltage during a transient state. At a time instance of 630 microseconds, the switching signals of the secondary full bridge are enabled, a measure that allowed to precharge the DC link capacitors, thus avoiding overcurrents, reducing total losses, and guaranteeing the integrity of the hardware. In a steady state, the mean value of the secondary DC link is 199.6 volts, extremely close to its reference value of 200 volts. The extended phase shift modulation is considered capable of reducing the values of circulating currents and conduction losses when a large amount of power needs to be transferred to and from each side of the DAB converter. In this sense, it is normally employed in medium-high voltage dynamic power systems in which the operating conditions are always changing. As in dual phase shift, 2 degrees of freedom are considered, D0 and D1, that is, the inner and the outer phase angles. However, the difference lies on the value of the gate signal applied to the semiconductor S7. Instead of adding the value of D0 to D1, as in dual phase shift, during the extended phase shift modulation, E7 is complementary to S5, that is, the influence of D1 is not considered on the second full bridge. This change on the value applied to the semiconductor S7 has a direct consequence on the voltage waveforms at the terminals of the high-frequency transformer. The voltage waveform on the primary side has 3 different voltage levels, while the voltage on the secondary side only presents 2. However, how it is possible to observe in the first image, the primary voltage is in advance of the secondary one, thus proving that the power flows from the primary side to the secondary side of the DAB converter. Applying this signal to the semiconductor S7, the waveform of the high-frequency control currents will be drastically different. Its peak values are extremely high, but, once again, with no mean value. Comparing the first to the second image, it is concluded that the current rises more sharply in the time intervals T1, T2, and T3, that is, when the primary and the secondary voltages of the high-frequency transformer assume their respective absolute maximum value. Despite presenting several advantages in medium-high power systems, the extended phase shift provokes worse results under light load conditions, as is the case. The operating range decreases, the reason why the obtained simulation results show higher current peaks and semiconductor stress. To mitigate this problem, a possible solution would be to increase the value of D1 or decrease D0. However, the regulation of the voltage on the secondary DC link to its reference value will be impossible to achieve. In turn, in the event of a possible change in the DAB operating parameters, increasing the value of the leakage inductance or the system's switching frequency, the current peaks of the primary and secondary currents will be lower. The regulation of the secondary DC link voltage during a transient state can be observed in the last figure. The image is coincidental with the moment when the capacitor pre-charges is finished. As it is possible to contemplate, the steady-state value of the voltage is 202.7 volts, thus resulting in a difference of 2.7 volts for the pre-established reference. Among the 5 control techniques contemplated in this paper, triple phase shift is considered the one with the best energy efficiency results, being capable of mitigating circulating currents and high reactive power values, change the root mean square value of the leakage inductance current, and consequently decrease the semiconductor stress. Such capability is obtained with the addition of a new degree of freedom, making a total of 3, D0, D1 and D2, a new interface angle existent between the legs of the second full bridge. The triggering gate signals applied to S3 and S5 are similar to extended phase shift and dual phase shift cases, adding the value of D1 and D2 respectively to the reference assigned to S1. As mentioned, the difference relies on the gate signal applied to S7, result of the sum of the value of D2 to the reference of the semiconductor S5. However, triple phase shift modulation presents greater implementation difficulty, since all the angles are independent from each other. During the realization of the simulations, it was concluded that a triple phase shift, due to the inclusion of a new degree of freedom, is considered more flexible from the previous phase shift variants. The value of D2 has direct influence in the time value that the voltage waveform of the secondary side of the high-frequency transformer assumes its maximum value, that is, 200 volts. In this way, it is possible to apply this modulation technique in light low power systems, which was not the case for the extended phase shift. However, the value of D2 is fixed and varied manually, that is, without any control strategy. The values of D0 and D1 are obtained with the previously explained control techniques. However, in situations that it is necessary to expand the zero voltage switching operation range, the value of D2 should be calculated based on appropriate control strategies. In this case, the benefit is lower than the cost and difficulty of implementation. Varying the time that the voltage waveform in the secondary side of the high-frequency transformer assumes its maximum value, the power transfer is carried out at a higher or reduced rate, depending on the application case. That fact can be confirmed by the analysis of the current waveforms, presented in the middle image. Its mean value is null, however the peaks are quite high, a situation that increases the stress in the power semiconductors. Once again, observing the first image, it is possible to conclude that the power flows from the primary to the secondary side, since the primary voltage waveform is in advance of the secondary one. Just like dual phase shift modulation, the primary and secondary voltage waveforms at the terminals of the high-frequency transformer present three different voltage levels. The last image shows the regulation of the secondary DC link voltage during a transient state. In steady state, the mean value of the voltage is 199.8 volts, extremely close to the pre-established reference of 200 volts, thus proving the veracity of the applied proportional integral control algorithm. In conclusion, it can be said that, throughout this paper, 5 modulation techniques that could be applied to control a dual-active bridge converter were studied and compared, namely, duty cycle modulation and 4-phase shift variants, single-phase shift, dual-phase shift, extended phase shift, and triple-phase shift. To compare and validate these modulation techniques, the simulation results were obtained with software PSIM from PowerSim. For each of these modulations, it was shown the triggering gate signals applied to the power semiconductors and the voltage and current waveforms in the high-frequency transformer and in the secondary DC link. The objective of presenting these waveforms is to validate the direction of the power flow in the DAB converter and the veracity of the applied control algorithms, namely the PI control technique that regulates the voltage on the secondary DC link. As mentioned, the simulation results were obtained for an operating power of 3.6 kW and a switching frequency of 100 kHz. Comparing the 5 modulation techniques, it was concluded that only single-phase shift, dual-phase shift, and triple-phase shift are suitable for this case. On the other hand, duty cycle modulation presents great limitations during power transfer, since the process is carried out at a very low rate. Conversely, extended phase shift modulation is more suitable for medium-high power and dynamic systems. As mentioned, the extended phase shift provoke worse results under light load conditions, as is the case. Lastly, Among single phase shift, dual phase shift, and triple phase shift modulation techniques, the last one is seen as the most flexible since it enables 3 degrees of freedom. However, its implementation difficulty is much higher and does not compensate the effort for this specific application case. After presenting the conclusions obtained through the analysis of the simulation results, I hereby finish my presentation. Thank you all for your attention.
Hello everyone, the paper that I'm going to present today is Smart Greenhouse Project, a sustainability focused learning experience for undergraduates. My name is Mohammad Upal Mahfouz and I'm an associate professor of engineering at the University of Wisconsin, Green Bay in Wisconsin, USA. Basically, this is a class project that my students Rick Kasky and Brady Conaher did last year as part of their classes, and I'm going to present the work on behalf of them. Okay, so as you know that recently the sustainability in education has been a major focus in education, engineering education curriculum. That is one of the main objectives of our work and motivation of our work. So in a STEM with project-based learning, sustainability is an important aspect to be incorporated, and we know that. We know that in the engineering curriculum these days we teach programming, introduction to programming, and supervisory control and data acquisition. So at the UW Green Bay we also teach these courses, and both of these courses they have an integrated project in each of these courses. So basically, as I said that I'm presenting on behalf of my students. This is a project work by 2 students in ET 142 and ET 342 classes that I used to teach every year. The motivation and the objectives of this work are, as you know, that scalable, sustainable food production is a challenge today, and this needs efficient resource utilization. This is one of the motivations of the Smart Greenhouse project work. The objective of this project is to create an automated system capable of growing vegetation with little human input by utilizing electricity, programming, and a microcontroller operation. So, and the other thing is we are going to incorporate sustainability focused education in our curriculum through this type of projects, and that is how the importance is. At the end of this work, we are also trying to explain or share our learning experience on sustainability focused education through this project. The Smart Greenhouse in the implementation and experimental part. So the students implemented the Smart Greenhouse with basically standard parts and components of a regular electronic shop. Various experiments were performed, and those experiments were microcontroller based programming controlled systems that the students built. The 3 main inputs of the system were temperature, humidity, and time. Temperature and humidity were provided via the DHT11 temperature and humidity sensor, while the date and the time provided via the RTC module. In this slide, we are showing the Smart Greenhouse control circuit, and not only that, there is a video. See reference 11 of our paper. There is a video uploaded that explains the the operation of the smart greenhouse project that will actually clear some of those things that have been described in this paper. This is one photograph from the project. This one shows the smart greenhouse overview. Again, the video will be giving you more details on the project itself. This is the DHT11 temperature and humidity sensor. Again, you can refer to the video that will give us some more details on the project work. This is the serial communication mimic diagram, the interface that the student built and worked on this to control the smart greenhouse operation. Again, you can refer to the video, reference 11 there. Now, in the next few slides, I'm going to share with you the learning experience we evaluated through this project, and those learning experiences are basically focused on sustainability. As you know, that incorporating sustainability in the STEM curriculum and our engineering curriculum is actually a very new approach, and that's why we thought of evaluating the learning experience through this project. So based on this slide and the following slides, the evaluation on learning experience is entirely based on the student feedback upon giving a set of questions where the students shared their comments, and this is based on that. First of these learning experience is the learning from the project itself, and first the project increased their programming knowledge and their knowledge of the microcontrollers and the circuits. They also learned the importance of data collection accuracy in order to provide efficient control of a system. They understood the importance of the data collection and its accuracy. They also learned that creating a control system could be very challenging at some time. Okay. Overall, we found that the students received the desired learning on programming knowledge from the project. Secondly, under the category of solving any technical issues, again based on the student feedback, students also responded that they often face unexpected technical issues in the project. They acknowledge that the technical troubleshooting is a major part of a complete learning of a subject matter. They created and used a testing program in order to troubleshoot the system. They reported that they had encountered troubles while trying to initiate control via the serial monitor, adding that while they were not able to solve the issue, they believed they were close to a programming solution to that problem. They acknowledged that the solutions to technical issues should consider a thorough investigation of the complete system. This is basically in order to make sure that the entire system performance, the system operation, is not disturbed by any technical issue in any of the parts of the system. Then, learning the subject matter itself. Again, this is based on student feedback. The students responded constructively in that the complexity of the programming aspect of the project reinforced the importance of a logical thought process when designing a product, and that actually helped their learning the subject matter. They also added that although initially the program seemed straightforward, they faced multiple new challenges as the program requirements grew based on practical needs. Okay. Then we thought of investigating on a real life problem. So whether we try to understand whether this smart greenhouse project addressed a real life problem, and this is based on a student feedback. The students responded positively, and they mentioned that the practical engineering problem that they were dealing with and exploring solution to, that actually was a real life problem. For instance, they mentioned that innovation in food production is very much a real-life practical engineering problem, and in that the Smart Greenhouse project had allowed them to investigate how people could produce food in a more localized and self-sustainable way. And actually this has a very good connection to a real-life problem, and that the students try to solve by using programming and microcontroller-based operations. The next thing is we try to self-evaluate the project, and again students try to self-evaluate the project. Again, this is entirely based on the student feedback on the self-evaluation of the project. The students suggested that the project helped them in learning the subject matter thoroughly. They also acknowledged that the project helped them greatly in understanding C++ programming language, because they were dealing with microcontroller operation with programming. They also mentioned that while the Smart Greenhouse was not identical to their initial vision, it came close to accomplishing everything that they set out to accomplish. So which made them believe that they were able to accomplish what they thought they would accomplish. Okay. Then finally, a very important aspect of the project is we wanted to experience sustainability, and we wanted to evaluate how our learning experience addressed sustainability in our work, and that is one of the major objectives of this work. So we asked the students a question whether the project addressed sustainability of any form in their project, and this is entirely based on the student feedback. So firstly, the students clearly suggested that the feedback from the students clearly suggested that the students were able to understand what sustainability is, the concept of sustainability is, and they were also able to define the concept of sustainability through their project. So they mentioned that the project touched on several different areas of sustainability. The most obvious impact was personal sustainability, and this was by allowing an individual to supplement their food supply by growing some or all of their own foods. Okay, by growing on their own. Okay. The smart greenhouse can be optimized to use the minimum amount of water necessary to irrigate the plants versus the largely wasteful watering that occurs in a farm field. More locally grown foods would also benefit the environment due to reducing the pollution that is produced by transporting crops long distances via various transportation vehicles. So, lesser carbon emissions is expected from growing foods locally. Okay. So in conclusion, we would like to say that sustainability focus in education is a significant challenge in STEM education curriculum these days, and nowadays incorporating sustainability in education is getting a momentum in education fields lately. So this is people are trying to incorporate sustainability in the education fields. Okay, and this is good for the future world that we live in. This smart greenhouse project, this is just an example of a sustainability focused learning experience. So there can be many other projects that address sustainability, and that could be incorporated in an engineering and STEM curriculum. That would be very much useful for with the target of incorporating sustainability in curriculum, in education curriculum. Okay. The design of the smart greenhouse should be useful among students with further improvements possible, especially in the direction of data collection and control strategies. Like I said, the students build a very simple way to demonstrate that in a course like programming and SCADA, such a project on a smart greenhouse can actually bring some concepts of sustainability in the classroom, and that was the objective of the work. However, the design can be improved by further investigating, especially in the data collection and the control strategies. So this is open for more research among interested students of the future. This is a set of selected references that we added in the paper. And finally, thank you very much for watching. And of course, if you have any questions, please feel free to reach out to the first two authors, Rick Kasky and Brady Conacher, or even to myself, and we will be very happy to reply back. And thank you very much for the opportunity, and I hope everyone will have a very good day. Thank you.
Thank you for coming today for this presentation titled Assessment of Renewable Energy Technologies Based on Multicriteria Decision Making Methods, Ocean Energy Case. My name is David Serrato. I'm here with you in the second EAI International Conference on Sustainable Energy for Smart Cities, representing the Research Group on Development in Operations Research, DINOP, of the Faculty of Electrical Engineering, and the Research Group on Energy Management Energética of the Faculty of Mechanical Engineering of the Technological University of Pereira, Colombia. This work was a collaborative study between the research groups mentioned and the Mining and Energy Planning Unit of Colombia, UPME. Now I am going to present you the introduction, the methodology, the results, and the conclusions. Introduction. It has been identified that countries conducting an energy transition to renewable energy technologies require an extended analysis to assess the feasibility for their implementation, identify financial risks, and settle emissions reduction. In Colombia, in the last several years, there have been more public policy strategies to expand alternative energy sources and accomplish the COP21 limits of 20% GHG reduction before 2030. In Colombia, Law 1715 of 2014 defines which energy sources are considered non-conventional. The objective of this law is the promotion of flows of capital on renewable energy projects which guarantee financial development and environmental sustainability. This law establishes that in Colombia these kinds of resources must be sustainable and must not be widely commercialized and used for large-scale power generation. Nuclear energy, biomass, geothermal, small-scale hydro facilities, wind, solar, and ocean energy are considered non-conventional and are covered by incentives and grants. Considering current issues in Colombia, such as constant high rates of demographic growth, financial challenges, and its environmental commitments of COP21 in Paris, the Mining and Energy Planning Unit (UPME) proposed a promotion program for renewable energy technologies with a goal of supplying 17% of the total energy consumption by 2030, exploiting renewable energy technologies such as solar photovoltaics, wind turbines, and new renewable energy technologies not including Law 1715 of 2014, such as ocean energy, vibrational energy, and green hydrogen could be a way to accomplish that goal. Today, the Mining and Energy Planning Unit of Colombia must identify and evaluate non-conventional energy sources that were not mentioned in the law to include them, if necessary. However, the inclusion of these energy sources necessitates financial and sustainable development. For that reason, in this study, a methodology based on multi-criteria decision making methods, MCDM, has been developed. This methodology is the result of a research project to assess comparatively new renewable energy technologies with renewable energy technologies currently used in the country based on technical, financial, and environmental criteria. The methodology allows for the identification of the best and the worst alternatives from the output ranking, considering the numerical value of criteria placed on the decision matrix and the dominance index output. The methodology was tested to assess the comparison of ocean energy technologies in Colombia. The energy matrix of OECD countries such as Iceland and Norway is composed by a high percentage of renewable energy sources due to the fact these countries have identified in the last decades the urgency for developing energy transition strategies aiming toward cleaner energy sources due to climate change issues. Nevertheless, the participation of coal, oil, and natural gas continues to be extremely high in most countries, so the necessity for better, wider, and more effective strategies to reduce the gross annual contaminant and GHG emissions have been identified. This is the case of the United States, as it shows. To improve energy security programs, OECD countries have been exploring multiple alternatives for the sustainable exploitation of non-conventional energy sources, both primary and secondary. Primary non-conventional energy sources are classified in renewable and non-renewable. Renewable energy sources are sources such as biomass, hydro, solar, wind, geothermal, ocean current, waves, thermal gradients, salinity gradients, seismic or vibrational, and waste. Non-renewable energy sources are sources such as peat, lignite, which are phases of the carbon formation, oil shale and tar sand, which are non-conventional sources of oil, gas hydrates, non-conventional energy sources of natural gas, metal ores and air minerals, which are sources mostly used for nuclear fusion processes. By the other hand, green hydrogen is considered a secondary non-conventional energy source or carrier. Among the energy sources mentioned by the Law 1715 of 2014 in Colombia, thermal gradients, salinity gradients, waves, tidal, and ocean currents have not yet been considered through finance projects despite the existence of their energy potential. On the other hand, geothermal and nuclear energy are sources highly promoted by industrialized countries, but in Colombia the financial, technological, and optimal conditions for their scale-up implementation have not been established. In addition, non-conventional energy sources such as seismic or vibrational and hydrogen have not been considered yet. To classify the best non-conventional energy technologies available for Colombia, the Technology Readiness Levels (TRL) is used. Technology Readiness Levels (TRL) is a classification scale of technologies designed by NASA to assess whether their emerging technology was suitable for space exploration. Nowadays, this scale is used by different industries to acknowledge the maturity and the readiness of a technology for its use in the real world. Technology is considered as emerging goes from TRL1 to TRL5. Technology is considered as growing goes from TRL6 to TRL7. Finally, technologies considered as mature goes to TRL 8 to TRL 9. It has been identified that ocean energy, a non-conventional primary energy source, is exploited by tidal stream, wave, thermal gradient, and salinity gradient technologies. Tidal has the highest TRL among them, and salinity gradients the lowest. Though hydrogen is exploited by internal combustion engines, turbines, and fuel cells using power generation, buildings, and light-duty vehicle applications, with TRL5 to TRL9, it was identified that the direct comparison with primary energy sources such as solar and wind is not an optimal standard. Unlike fuel cells, vibrational energy technologies such as piezoelectric and electromagnetic devices were not considered in the assessment due to its TRL4 and emerging readiness level. Now, the methodology. The methodology proposed aligning with the Colombia energy market should contain the following characteristics: being a tool that supports the development of public policy, having the ability to conduct a comparative assessment of the renewable energy technologies, considering technical, financial, and environmental criteria simultaneously, having the ability to assess multiple scenarios associated with variations of energy markets. In this study, a methodology for the evaluation of renewable energy technologies in Colombia is proposed. This methodology has been validated by the Mining and Energy Planning Unit of Colombia. This proposal consists of 3 phases being conducted in sequence: Phase 1, mapping the problem; Phase 2, performance assessment; and Phase 3, multicriteria decision making method. In Phase 1, the evaluation case is defined, and the technical, financial, environmental, social, and/or sociopolitical criteria are selected, considering which criteria are most used for the assessment of renewable energy technologies. The criteria are selected by the AHP method, which considers the judgment of experts from private and public sectors. The scenarios are established and the assignation of attribute for criteria is conducted. The objective, the decision makers, and the alternative energy sources were identified. Moreover, according to literature, the evaluation criteria for renewable energy can be divided into 4 main categories: financial, technical, environmental, and social dimensions. Criteria such as capital cost, operation and maintenance cost, levelized cost of energy, power capacity, efficiency, job creation, welfare improvement, social acceptability, emissions reduction, and land use are commonly considered in renewable energy technologies studies. Among them, capital cost, levelized cost of energy, and the gross annual GHG emission reduction were chosen as the criteria for this study in accordance with the results of the AHP method and the suggestion of the Mining and Energy Planning Unit of Colombia. Among these, GHG emission is one of the most widely used criteria in evaluating sustainability of renewables. However, in order to enhance the spectrum of the assessment, the following criteria were considered: the financial, technical, and environmental scenarios regarding power capacity, technology readiness levels and capacity factor regarding technology, capital cost and levelized cost of energy in terms of financial criteria, and gross annual GHG emission reduction in terms of environmental impact. In phase 2, the financial and technical parameters for each project are defined, such as the electricity exported to grid, electricity export revenue, debt, and equity. Moreover, there are defined financial indexes, such as the net present value, the benefit cost ratio, the annual life cycle savings, the simple payback period, the equity payback, and the levelized cost of energy. Additionally, environmental indexes related to GHG, such as the gross annual GHG emission reduction, are assessed. Based on these indexes, a feasibility assessment is conducted. In phase 3, the comparative assessment of renewable energy technologies for the evaluation case and scenarios is conducted. The weights of criteria are computed by a method based on the calculation of Shannon's entropy. So, by the application of the Multicriteria Decision Making Methods (MCDM), the best and the worst alternatives from the output ranking are identified. Finally, the criteria which cause more variability on decision making via sensitivity analysis based on the evaluation of the scenarios are identified. Note that criteria used in the MCDM to evaluate alternatives are as follows: technological readiness, power capacity, investment cost, levelized cost of energy, and emission reduction. Previously, in phase 2, financial indicators with which it is possible to execute an analysis of the financial performance of the projects are used. This allows for the identification of the specific sales price value of energy that guarantees the alternatives that are evaluated in the method. On the other hand, even though some of the selected criteria to execute the evaluation are interdependent, like LCOE, the capacity factor, and CAPEX, diverse studies that have selected these interdependent criteria did not assign importance to this dependence. Now I am going to present you the results. Here I present you the decision matrix used as an input in the MCDM method. Values of criteria were obtained by 3 ways, given by UPME, calculated by simulations using the red screen software, and by references. Based on the data of the decision matrix, Shannon's entropy was used to calculate the weights of criteria. It means the relative importance of each criterion. Since the criteria weights significantly cause changes on the rank, a sensitivity analysis was conducted to reveal the ranking alternative changes due to the variation of criteria weights. To accomplish that, the weight value of criteria for each scenario was adjusted to grant 80% of the sum of criteria of the same category, meaning the remaining 20% for the other scenarios and criteria were reduced or increased proportionally from the base case to complete the sum equal to 1. It was found that the weights of capacity factor and TRL are much smaller than the others. This could be explained considering that a small numerical difference among values of a criterion for each alternative means a lower probability of obtaining information, higher entropy, and lower weight. So power capacity, investment cost, LCOE, and GHG emission reduction criteria are much better for decision making in this case. Nevertheless, capacity factor and TRL are important for the overall analysis, considering that for Colombia this assessment is one of the first steps for the development of a baseline of renewable energy technologies and sources, such as ocean energy, which is a renewable energy source not yet considered in the energy matrix. Now I present you the results of the economic, technical, and financial assessment. In the table above is presented the values for the electricity exported to grid, the electricity export revenue, debt, and equity of the alternatives. The method Prometheus was applied to conduct a relative comparison of the financial performance of the projects. Likewise, MCDM methods, Topsis, Bicor, and Prometheus were applied to the decision matrix presented before. A sensitivity analysis was conducted based on the weight value of criteria for each scenario and the method used. The parameters and the results of the financial and the environmental performance assessment were used to grant the numerical values of criteria, such as the LCOE and the gross annual GHG emission reduction. A debt ratio of 70%, a debt interest of 7%, a debt term of 15 years, a discount rate of 9%, and an escalation rate of 2% were considered for the performance assessment of the projects. Computing a proposed two-step subroutine, the financial indexes for the projects were calculated. In the table below, I present the value of the financial indexes for each project which is considered. To conduct an extended financial performance assessment, weight of criteria, in this case the net present value, the benefit cost ratio, the annual life cycle savings, the levelized cost of energy, were calculated by Shannon's entropy and data was computed by Prometheus. It was found that tidal range has the best financial performance and ocean current the worst. It was identified that the ALCS was the most important criterion for financial performance assessment. By the other hand, the gross annual GHG emission reduction of the alternatives was calculated. The GHG emission of the base case was and proposed cases were calculated considering an emission factor of 0.548 tons of carbon dioxide per megawatt hour. The base case was computed considering the power generation by a natural gas thermal power plant and electricity generation efficiency of 38% and transmission and distribution losses of 5%. It was found that tidal range presents the highest emission reduction. It is explained considering that emissions are dependent on the electricity exported to grid. So, due to tidal range has the highest power capacity, it is expected the highest rate of emissions and the gross emission reduction. In phase 3, data was computed by 3 MCDM methods, Topsis, Bicor, and Prometheus. The ranks obtained from the methods considered were similar, although not entirely equal. However, this issue points out the validity of the algorithms used. It is observed that tidal range is the best alternative and ocean current the worst for all the scenarios. This could be explained considering the difference in the power capacity being higher for tidal range. Since higher power capacity eventually imply higher electricity exported to grid for similar capacity factors and higher electricity exported to grid leads to higher gross annual GHG emission reduction for similar GHG emission factors and lower levelized cost of energy for similar investment cost values. even though the objective of this study was not doing a comparison among MCDM methods. These were used to validate the results and the ranking the alternatives obtained. Note that these indicators are highly dependent on the sales price of energy annual rate. In other words, there is a guarantee that the projects for this initial simulation are financially viable, given that the sales price of energy for the solar and wind project was calculated at $100 per megawatt hour, and the ocean wave, tide, and currents project were calculated at $300, $200, and $600 per megawatt hour, respectively. The assumption is that the price at which each project can sell energy is within a reasonable range, which allows them to be competitive within the national energy market. However, despite the fact the levelized cost of energy might appear attractive when compared with estimated typical mean values for a specific technology, it may not be the case due to the two differences in the order of magnitude in the sales price of energy. Now I am going to present you the conclusions. The assessment of renewable energy technologies can be conducted by multi-criteria decision-making methods considering technical, financial, and environmental criteria as a tool to reduce financial risks and guarantee the objective goals of renewable energy projects. The comparative assessment of ocean energy technologies with renewables such as solar and wind in Colombia was considered. A methodology based on three phases was proposed. First, mapping the problem. Second, performance assessment. Third, multi-criteria decision-making method. The results of the financial and the environmental performance assessment were used to grant the numerical values of criteria such as the LCOE and the gross annual GHG emission reduction. It found that the gross annual GHG emission reduction percentage is the same for all the alternatives, but tidal range exhibits increased gross annual emission reduction due to its high power capacity. Likewise, tidal range exhibits the best financial performance among the alternatives. Unlike tidal range, ocean energy exhibits the worst environmental and financial performance. In phase 3, data was computed by three MCDM methods, Topsis, Bicor, and Prometheus 2. The ranks obtained from the methods considered were similar, although not entirely equal. However, this issue points out the validity of the algorithms used. Finally, for similar power capacity, solar energy would be a better alternative than tidal range, considering that solar's financial performance was better than tidal range, even though the power capacity of solar was approximately 65% lower. Thanks.
Hi, my name is Clayton Magalhães Freitas and I'm here to present you the paper called Mitigation of Low-Frequency Oscillations by Tuning Single-Phase Phasor Locked-Loop Circuits. The other authors of this publication are Mrs. Diana Lessa and Professors Michel Cho and Luis Monteiro. All the authors of these articles are from Rio de Janeiro State University, and to be more specific, Professors Michel Cho and Luis Monteiro are from the postgraduate program in electronic engineering. Now I'm going to present you how this presentation might be divided. I pretend to go through 5 steps. First of all, talking about the introduction, and afterwards presenting the POL structures considered in the paper. I'm also presenting here the proposed approach for tuning the internal parameters and the simulation and experimental results of our publication. And finally, I'm going to present you some conclusions of the article. So let's start with the introduction. A phase-locked loop circuit, or simply a POL, is either a control algorithm or electronic circuit that captures the phase and fundamental components of an analyzed signal. This block diagram will basically outlines the general structure of a POL. It comprises 3 major blocks: a phase detector, a loop filter, and a VCO. The phase detector, for instance, is in general a nonlinear function used to capture and track the phase and frequency of the input signal. As for the loop filter, it's in general a linear function used to block off all the undesired components from the previous signal. The VCO, which stands for Voltage Controlled Oscillator, is basically a circuit or algorithm that will be used to synthesize the sinusoidal signals that match the fundamental component of the analyzed signal. We could say that POL were initially considered for communication systems, but right now there are several other fields of application, such as power electronics and power systems. When it comes to these last 2 fields of application, we could say that POLs are used for synchronizing grid-connected converter and also for identification of power quality problems and power quality related phenomena. So, considering these 2 applications, POLs could be either 3-phase or single-phase, or to be more specific, POLs could present a 3-phase structure or single-phase structure. In fact, 3-phase POLs are simpler, but I will not be discussing these longer in this presentation. Now I'm going to present you the POL structures considered in this paper. First of all, it's important to notice that we dealt only with single-phase application, and for that we consider 3 different POL structures. The first of them is the enhanced POL, or simply EPOL, which is basically composed of 2 control loops. One of them focusing on the amplitude of the analyzed signal and the other in the phase. In general, the amplitude loop uses an integral controller, whereas the phase loop considers a PI controller. It's important to notice that the standard EPOL doesn't have this notch filter here. In fact, the notch filter considered in this POL is due to cope with the double frequency components that may appear in the error signal, this one right here, whenever we have distorted input signal. The next POL structure considered in this work is based on second-order generalized integrator, or simply a SOG POL. The idea behind the SOG POL is combining a regular synchronous reference frame POL, which is basically this part here of this block diagram, with a second-order generalized integrator, which is basically this part of the circuit. The SOG, in this case, produces a pair of orthogonal signals that could be used as input for this regular synchronous reference frame POL. This POL suffers also from the same problem presented in the previous POL. Whenever we have distorted input signals, some of the control signals may present double frequency components, such as the VQ. That's why we considered also the use of a notch filter. In the same way as the previous POL, this notch filter is adaptively adjusted to tackle the second order component of this signal, so that this distortion doesn't flow inward the POL, it doesn't compromise the production of the output signal. The third POL structure considered in this work was the APF-POL, and this acronym, APF, stands for All-Pass Filter, which is basically this block diagram presented in this part of the slide. The idea behind the all-pass filter is to give a 90-degree shift in the input signal. In this way, it's possible for us to obtain a pair of orthogonal signals, in this case V alpha and V beta, that could be used as input for a regular synchronous reference from POL. The same way as the previous POL, whenever we have distortions in the input signal, these harmonic components may flow inward at the block diagram and end up causing oscillations in double frequency at variables such as VQ. That's why we also consider here a notch filter with the same idea of the notch filter considered in the previous POLs, just to cope with this oscillation and guarantee a better performance of the POL. Now that I present all the three different phase locker loop circuits, we could proceed to the next topic, which is basically the proposed approach for tuning the internal parameters. But before starting the discussion, it's important to mention that a general approach for adjusting the control gains in the POLs, such as the ones presented in this paper, is based on the linear control theory. In this case, a set of linearized models are used to represent the POLs, and all the nonlinear effects and characteristics are disregarded. A weak point in this approach is the fact that the linearized models are only valid for small signal perturbations. Consequently, it's not possible to guarantee that the performance obtained during the tuning procedure will be reproduced in real-world applications. So, rather than considering linearized models and linear control theory, we decide to adjust the control gains through a searching process. In this case, we consider settling time t and the total harmonic distortion THD as performance parameters, and we investigate the effects that different values or different combinations of control gains cause in these two performance parameters. Among the results, we choose those which presented settling time lower than 100 milliseconds and THD lower than 2% to present them in the following charts. It is also important to mention here that we consider during this process of searching an input signal comprising several different harmonic components. This was basically for see whether or not the POL structures are able to only extract the fundamental component of the input signal, and of course to test whether or not the notch filter considered in all of the three POLs is effective or not. I'm going to start with the EPOL. But the EPOL presents two loops within its circuit. One loop intended to track the amplitude of the input signal and other for the phase. It's not possible to decouple both the loops, so we have to tune all the three parameters, all the three control parameters, three control gains together. In this case, we follow this approach right here. We decided to test the performance of the POL under four different circumstances, one of them for each value of the proportional gain of the phase loop. Within each one of these conditions, we consider a variety of values of integral gains for the phase loop and for the amplitude loop. And it's possible to see in these results that the case D, where the proportional gain of the phase loop is 34, it presents lower values of settling time. Next up, we analyze the phase loop of this same POL using the same consideration presented in the previous slide. But here it's important to notice that the difference of the gains play a more important role. We could see that only a small region of the spectrum produce convergence time or settling time under 4 milliseconds, whereas in almost the entire spectrum, entire range of integral gains, in all the 3 cases presented here, the settling time goes over 4 or 5 milliseconds. The SOG PLL, differently from the EPLL, presents a single control loop, which is intended to track the phase of the input signal. So we have only 2 parameters to adjust, the proportional and the integral gains. You vary these values in a large range and you obtain this result right here. It's important to notice that in most parts of this spectrum, most parts of this range, the settling times reached over 8 or 9 milliseconds. Only a small portion of this range obtain values under 6 or 7 milliseconds. It's important to notice that this SOG PLL, or to be more specific, this single phase PLL is lower than the previous one, is lower than the PLL considering the enhanced structure. As for the last PLL, the one based on an all-pass filter, we also got a similar response as the one obtained for the SOG. Only a small portion of the range of the proportional and integral gains resulted in fast convergence time, whereas in most parts of this range, the PLL took about 100 milliseconds to converge to a steady state condition. This figure in the right side here presents a zoom in this part of this spectrum. We could see here that the results are comparatively better than the SOG because it could also obtain convergence time under 4 milliseconds. After conducting the tuning process, we decided to pick up the best results from this analysis to present some simulation and experimental tests. This is the basic idea in this next part of the presentation. So this slide kind of summarizes the general idea. For simulation, we consider the Octaves as the main program used to simulate the PLL structure. And for coding the PLLs or for representing the PLLs in the Octaves, we use a code-based approach in which we transfer the original models of the PLL from Laplace domain into Z domain and afterwards into difference equations, so that we could come up with a set of equations that represent the dynamics of the internal states of each one of the PLLs. As for the experimental test bed, we consider this block diagram right here. The core of our experiment is the ZSP board represented in this part of the diagram. It basically comprises a F28335 DSP from Texas Instruments, which is in fact a standard DSP used in power electronic application. It has 150 MHz clock and it has several analog to digital converters and several interfaces for PWM signals. For analyzing the dynamics of the internal signals of each one of the 3 PLLs considered in this work, we decided to externalize them through PWM interface. The idea, or the main idea, was basically modulate the PWM signals with the information from signals such as VQ or omega in other internal signals of the PLL. Of course, these PWM signals present high frequency content that is eliminated through a low-pass filter. But it's important to notice here that as the frequency of the PWM signals are 20 kHz, the cutoff frequency of this low-pass filter is high enough not to cause any significant effects on the dynamics of the analyzed variables. Afterwards, the output of the low-pass filter is fed into an oscilloscope so that we could print here some of the major experimental results. Now that I present the general idea behind the simulations and experimental tests conducted in the research, we may proceed and present the results itself, starting off with the EPLL, and to be more specific, with the simulation result for the EPLL. In this graph here, I present the input and output signals obtaining during the simulation. This input signal right here, presented in blue color, is a high distorted signal used to test the performance of the PLL. As you can see in the Fourier spectrum, the input signal presents a fundamental component at 6 Hz and 3 other harmonic components, the third order, the fifth order, and the seventh order. Analyzing this graph here, we could see that the output signal at orange in this graph presents a sinusoidal shape, indicating that the fundamental component of the input signal was correctly tracked. This affirmation could be corroborated by analyzing this graph of the spectrum domain, of the frequency domain, showing that the output signal presents only a component at 60 Hz, matching exactly the amplitude of the fundamental component of the input signal. Notice that there is a small third order harmonic at the output signal, but it's fair to say that it's quite smaller than the original present in the original signal. We also present here some of the inner signals, such as the errors of phase and the errors of amplitude, or the error of amplitude. It could be seen in this graph right here that there is a small difference between these two variables, because one of them corresponds to the input of the notch filter considered in the phase loop, and the other one corresponds to the output of this notch filter. There is a small difference showing that the notch filter somehow reduced the amplitude of the second order oscillation present in this signal. It's also possible to notice by these results that the loop phase, phase loop is faster than the amplitude loop, because as you can see right here, the amplitude signal error reach a steady state condition in about 4 milliseconds, whereas the phase error signal reached steady state condition in less time than 2 milliseconds. In this slide here, I present the experimental results. Following the same approach of the simulation, we considered a high distorted input signal presented in this graph at the color green. As you can see, this signal, which Fourier components are presented in this graph right here, also presents a fundamental component, a third order, a fifth order, and a seventh order harmonic components in it. It's also possible to see that the output signal, the signal tracked by the PLL, presents a sinusoidal shape, and this could be confirmed by analyzing its Fourier spectrum, showing that it presents a major component at the fundamental frequency, but also presents a small component at the third order harmonic. But this is not a great issue. When it comes to the inner signals, we could see the same rule presented in the simulations. The phase loop is faster than the amplitude loop, and in this case right here, the amplitude loop presents higher oscillations than the phase loop. This difference is due to the fact that we didn't use a notch filter in the amplitude loop. So we can now go to the SOG-PLL results, starting off with the simulation. I'm going to be a little bit faster here because all the things related to the input signal are the same for the 2PLF. To be more specific, for the 3PLF. And we can see in this graph right here that the SOG-PLL was able to track the fundamental component of a high distorted signal without presenting any significant distortion in it. These results can be better analyzed looking through the FFT spectrum. You can see that the output signal comprises only a fundamental component, and this fundamental component also matches the fundamental component of the input signal. This graph right here presents some of the inner signals of the SOG-PLL. In this case, the input and output of the notch filter. VQ is the input of the notch filter, and it presents a larger oscillating component in comparison to the signal that appears at the output of the notch filter. Moving toward the experimental results of the SOG-PLL, we see in the first graph that the output signal in yellow basically comprises the fundamental component of the input signal, which is in green. These two graphs right here present the FFT components of both input and output signals. As previously mentioned, the input signal comprises several harmonic components, and the output signal presents only the first order or the fundamental component of the input signal. We also present in this slide the outputs of the second order integrator, which is basically a pair of orthogonal signals such as the one presented here. Now we can go for the last PLL structure considered in this work, the APF-PLL. Starting from the simulation results, we can see in this graph right here that the output signal presents a sinusoidal shape and tracks the fundamental component of a high distorted input signal. This comparison could be better understood in the frequency domain, when we can see that the output signal presents only the fundamental component of the input signal and doesn't present any of the harmonic content in the original signal. We also present here the input and output signals of the notch filter used in the APF. We can see here a small difference between these two signals due to the fact that the notch filter filters out the second order harmonic component, which is commonly found in this signal right here. Moving for the experimental part of the test, we can see that just like the other PLLs, the APF was able to produce a sinusoidal component matching the fundamental component of a high distorted signal. In the same way, we can see in the FFT domain that the output signal presents a major component at the fundamental frequency, but it also presents two other components different from the previous PLLs, one of them in the third order and the other in the fifth order. But it's not a great shoe due to the fact that the amplitudes are quite small in comparison with the fundamental components. We also provide here the results for the input and output of the notch filter. Notice that the input signal of the notch filter in green in this chart right here presents larger oscillating components than the output signals of this element. As explained before, the notch filter filters out the second order harmonic component, and that's why we have this difference between these two signals right here. In this table, I present the main results of our analysis. We have to compare here two important aspects, the settling time and the total harmonic distortion of the output signal. When it comes to the settling time, the EPLL was the one with the best performance. In this case, it took it about 41 milliseconds at the simulation and about 30 milliseconds in experimental results to reach a steady state condition, whereas in the other two cases we have something like 66 milliseconds and about 50 milliseconds for the APF-POL. When it comes to the total harmonic distortion, on the other hand, the best options were the SOG and APF-POLs. They both achieved the results under 0.7%, whereas the EPLL achieved the result in about 1.6%. Now I'm going to present you the conclusions of our work. The first conclusion is that the notch filter considered in all the three PLLs was able to attenuate the second order harmonic oscillation in the inner signals of the PLLs. We also concluded that the search method was able to provide us a range of control gains which could match with our initial constraints. And finally, the simulation and experimental results show TAD and settling time were under these constraints, these initial constraints, which was 2% for TAD and 100 milliseconds for the settling time. Thanks for your attention. In this slide, I present some of our emails and contacts if anyone have any doubt.
Hello everyone, my name is José Salgado. I'm going to do the presentation of our paper entitled Efficiency Comparison of Different DC-DC Converters, Architectures for a Power Supply of a LiDAR System. Autonomous vehicles are identified as the main booster in terms of future intelligent transport in smart and sustainable cities. Within this context, LiDAR, which means light detection and ranging, is one of the key sensing technologies required to enable partial or fully autonomous driving. Specifically, LiDAR is an active remote sensing method that works on the same principle of sonar, but using laser pulse to build a 3D model of the environment around. Internally, a LiDAR system is constituted by several parts, such as a laser source capable of transmitting pulsed or continuous light, a low noise high-speed receiver capable of detecting and processing the reflected light beam, and a lower power controller unit, where the power supply is a common system to all the parts, which must guarantee the proper voltage and power levels. This paper presents a comparison between three different architectures for the power supply of LiDAR, by reorganizing the same DC converters in the three different architectures. For the requirements of the LiDAR, this particular LiDAR system requires a total power of 50 watts for the three voltage levels, as shown in the table. In this case, for 3.3 volts, it needs an operating power of 17 watts, for 5 volts 5 watts, and for 12 volts 28 watts. it will be considered a minimum input voltage of 15 volts and a maximum input voltage of 65 volts for the power supply. The topology adopted in the scope of this paper is the synchronous buck switched mode power supply, for short SMPS, which is a modified version of the conventional buck converter SMPS, in which the diode is replaced by a second power switch, in this case a MOSFET, minimizing the diode conduction losses and thus improving the conversion efficiency. The synchronous buck converter has two operating modes. In mode 1, Q1 is on while Q2 is off. Therefore, the current in the inductor increases. In mode 2, Q2 is on and Q1 is off, providing a path for the energy stored in the inductor to flow through the load. The two MOSFETs, Q1 and Q2, are alternatively switched according to the PWM signal generated by the controller IC. The three synchronous buck converters considered will be described in the next slides. The LM5146Q1 is a switching controller with a wide input voltage ranging from 5.5 volts to 100 volts and a wide adjustable output voltage from 0.8 volts to 60 volts. It allows a maximum output current of 30 amperes and the switching frequency has a minimum of 100 kilohertz and a maximum of 1000 kilohertz. The LM5116 is also a switching controller. It has a wide input voltage ranging from 6 volts to 100 volts and an adjustable output voltage from 1.2 volts to 80 volts. It allows a maximum output current of 20 amperes and the switching frequency is from 50 kilohertz to 1000 kilohertz. This one is a switching regulator, the TPS548A20, has a input voltage ranging from 1.5 volts to 20 volts and an output voltage from 0.6 volts to 5.5 volts. And it has integrated MOSFETs. So in comparison to the other ones needed the external MOSFET. And the maximum output current is 50 amperes. In this case, the switching frequency can be from 250 kilohertz to 1000 kilohertz. It will be considered three architectures, the parallel, the cascade and the hybrid. The parallel architecture on the left side, all the three DC-DC converters share the same input, in this case 15 volts to 65 volts. The cascade architecture, in the middle, in red, only the 12 volt DC-DC converter has the input voltage of 15 volts to 65 volts. In this case, the 5 volt DC-DC converter has 12 volts as input, and the 3.3 volt DC-DC converter has 5 volts as input. On the right side, it has four hybrid architectures, but in this case, in the top left one, the 12 volt DC-DC converter has the input voltage of 15 volts to 65 volts, and then the 5 volt and 3.3 volt DC-DC converters will share the same input, in this case 12 volts. To demonstrate the methodology used in the efficiency comparison, and for the sake of simplicity, in this work only one of the hybrid variants is used in the comparison with the parallel and cascade architectures. It was selected this architecture, in this case the top left one of the hybrid architecture, because it seems that it guarantees better efficiency since the voltage in the first stage is nearest of the output voltage. The input and output voltage, and as well as the output current and the converters used in each architecture are presented in this table. The converters at each architecture were chosen taking into account the efficiency of conversion and the necessary input and output voltage at each stage, as well as the necessary current. This means that For different architectures, even for the same voltage level, different converters were used. For the software used and the procedure, it was used the software WeBench Power Designer from Texas Instruments to design and simulate the circuit. Every architecture was individually simulated at an ambient temperature of 25 degrees. The architecture efficiency was obtained for the maximum operating power required at each output voltage level, also considering the highest possible voltage at the input, corresponding to the most critical situation. The switching frequency of each converter was selected in order to achieve the best performance. In the parallel architecture, the DC-DC converter, all the DC-DC converters share the same input voltage, in this case ranging from 15 volts to 65 volts. According to the graph displayed, the obtained efficiency of the 3.3 volt for an output of 5.15 amperes and an input voltage of 65 volts, the worst case, is approximately 84.5%. For the same output current but with lower input voltages, the efficiency is higher, 88% for an input voltage of 40 volts and approximately 93% for an input voltage of 15 volts. For the 5 volt DC-DC converter, the obtained efficiency for an output current of 1 ampere and an input voltage of 65 volts, the worst case, is approximately 75%. As in the previous converters, for the same output current with lower input voltage, the efficiency is higher, 82.5% for an input voltage of 40 volts and 92% for an input voltage of 15 volts. For the 12 volt converter, with an output current of 2.33 amperes and an input voltage of 65 volts, the efficiency obtained is approximately 95.2%. Once again, for the same output current with lower input voltage, the efficiency is higher, namely 96.2% for an input voltage of 40 volts and 98.2% for an input voltage of 15 volts. Taking into account the efficiency values of each conversion, the overall efficiency for the parallel architecture, considering the most critical situation, is given by the next equation, resulting in a total value of 88.97%. For the cascade architecture, in this case for the 3.3 volt DC-DC converter, according to the graph displayed, the expected efficiency for an output current of 5.15 amperes and an input voltage of 5 volts is approximately 97.95%. The output current required at 5 volt DC-DC converter for the 5 watts requested by the LiDAR system and to power the 3.3 volt DC-DC converter is 4.47 amperes. According to the graph displayed, the expected efficiency of the 5 volt DC-DC converter for this current and an input voltage of 12 volts is approximately 97.9%. The output current required at 12 volt DC-DC converter for the 28 watts requested by the LiDAR system and to power the 5 volt DC-DC converter is 4.24 amperes. According to the graph displayed, the expected efficiency of 12 volt DC-DC converter for an output current of 4.24 amperes and an input voltage of 65 volts, the worst case, the efficiency is approximately 96.25%. Again, the efficiency is better for lower input voltages, namely 97.25% for an input voltage of 40 volts and 98.7% for an input voltage of 15 volts. The overall efficiency for the cascade architecture, considering the most critical situation, is given by the equation with a total value of 94.67%. For the hybrid architecture, and according to the graph displayed, the the expected efficiency of the 3.3 volt DC-DC converter for an output current of 5.15 amperes and an input voltage of 12 volts is approximately 97.4%. For the 5 volt DC-DC converter for an output current of 1 ampere and an input voltage of 12 volts, the efficiency obtained is 97.4%. The output current required at 12 volts at the 12 volt DC-DC converter for the 28 watts requested by the LiDAR system to power the other two converters is 4.22 amperes. According to the graph displayed, the expected efficiency of the 12 volt DC-DC converter for an output current of 4.22 amperes and an input voltage for the worst case 65 volts is approximately 96.25%. As in the former cases of the 3.3 volt and 5 volt DC-DC converters, the efficiency is better for lower input voltages, namely 97.25% for the input voltage of 40 volts and 98.7% for an input voltage of 15 volts. The efficiency for the hybrid architecture is given by the equation displayed with a total value of 95.13%. The efficiency must be as high as possible to prevent unwanted power losses and optimize the LiDAR system performance. According to the detailed study performed focusing on the efficiency of the three possible architectures and presented in the previous items, the obtained values of the efficiency for each architecture are summarized in this table. By comparing the three architectures for the same conditions of operation, it was possible to identify that the hybrid architecture presents the best obtained efficiency, with a value of 95.13%. Nevertheless, it was also possible to analyze that the cascade architecture, with an efficiency of 94.67%, is also a good alternative to the hybrid architecture for the LiDAR system, since the obtained values are very similar to the cascade architecture. The parallel architecture presents the worst efficiency with a relevant difference when compared to the other architectures, demonstrating that it's not a good alternative for the LiDAR system due to the high efficiency required. For conclusions, this paper presented a comparison between three different DC-DC converter architectures for a LiDAR system. The architectures under comparison were three DC-DC converters linked in a single input and multiple outputs structure, three DC-DC converters linked in a cascade, and two DC-DC converters in a single input, multiple output structure, and in a cascade with the third one. The obtained results for the considered application show that the hybrid architecture has highest efficiency, in this case 95.08%, considering the higher possible voltage at the input, 65 volts, and the maximum operating power of this particular LiDAR system. The same methodology could have been used considering all possible hybrid variants architectures. The final best choice, the best efficiency, will depend, in a general case, on the individual efficiencies exhibited by the DC-DC converters and the required power losses associated to each specified output voltage. Thank you very much for your attention.
Hi everyone, my name is Katia Oliveira and I'm going to present the paper entitled A Single-Phase Current Source Converter for Interfacing an Electric Vehicle and a Renewable Energy Source. During the presentation, I'm going to introduce the subject of this paper. Then I'm going to describe the adopted topology that is possible a solution for the interface of electric vehicles and renewable energy sources. In this case, The approach to topology is based on a current source converter that it will be described more in detail. In order to obtain the correct operation of the current source topology, it was studied a control algorithm that it will be also described in detail during the presentation. Then, it will be presented all simulation results that show the correct operation of the entire topology in different operation modes. Finally, the main conclusions will be presented. The increasing greenhouse gas emissions caused by conventional vehicles is a huge concern. Electric vehicles is an efficient solution for a more sustainable mobility. Moreover, the electric vehicles allow to store the energy in periods where the renewable energy source production is excessive, to deliver the energy back to the installation in order to balance the power management and consumption. The integration of the electric vehicles and renewable energy source in a power grid can introduce power quality problems, such as current harmonics and low power factor. Thus, the interface of the electric vehicle and renewable energy source with the power grid is performed by an AC-DC converter and a DC-DC converter. An AC-DC converter is responsible to guarantee sinusoidal currents with low harmonic distortion and unitary power factor. A DC-DC converter ensures a controllable voltage and current of the DC interface. This paper proposed a single-phase current source converter combined with a hybrid converter for interfacing an electric vehicle and a renewable energy source. The interface with the power grid is performed through the current source converter and presents the following operation modes. Operation as shunt-active power filter in order to compensate the current harmonics and to obtain a unitary power factor. Operation as electric vehicle charger, where the electric vehicle is charged with power from the power grid. And operation as electric vehicle discharger, where part of the stored power is injected into the power grid. Operation as a renewable energy source interface, injecting power into the power grid, and combined operation of the previous modes. Now I'm going to describe in detail the adopted topology based on a single-phase current source converter. Here, it is presented a block diagram that shows the current source converter combined with a hybrid converter for interfacing an electric vehicle and a renewable energy source. Regarding the electric vehicle charging, several controls can be considered in order to preserve the battery's life cycle. In this paper, it was applied the constant current and constant voltage method because of its simplicity and easy implementation. On the other hand, regarding the renewable energy source interface, also several control algorithms can be considered, such as the maximum power point tracking, MPPT, based on the perturb and observe strategy. As it can be seen, the topology consists of a current source converter and a hybrid converter. The AC-DC converter is required for interfacing the power grid with the DC link to compensate the current harmonics in the power grid and obtain a unitary power factor. On the other hand, the hybrid converter is bidirectional converter. The aim of this converter is interfacing the electric vehicle, allowing the power absorption or injection in the power grid, and interfacing the renewable energy source, extracting the maximum power. Proposed control algorithm. This figure presents the control algorithm for the single-phase current source converter interfacing the electric vehicle and renewable energy source. The control algorithm includes the control theory for the shunt-active power filter operation performed by the current source converter, the charging of the electric vehicle using the constant current and constant voltage method, and the extraction of the maximum points of the power from the renewable energy source through the MPPT control algorithm. The management of the power from or for the electric vehicle and the renewable energy source is made by the hybrid converter. The operation of the shunt active power filter is made before and during the charging and discharging of the electric vehicle and the extraction of the power from the renewable energy source. For the correct operation of the shunt active power filter, it is required a method of synchronization with the power grid. In this case, it is used the EPLEL algorithm. The DC-link regulation (PREG) is obtained with a PI controller, where the input signals are the DC-link current, ADC, and its reference. Based on the EPLEL and the load current, it is calculated the compensation current through the FPD theory. The commutation of the power semiconductors of the current source converter is obtained from the modulation block of the shunt active power filter. On the other hand, the hybrid converter is controlled for the electric vehicle charging following the two stages of the constant current and constant voltage method and for the electric vehicle discharging. As it can be observed, the variables needed to control the hybrid converter are the electric vehicle current, the electric vehicle reference current, and the electric vehicle voltage. Moreover, it is measured the voltage and the current on the renewable energy source for the calculation of the power provided by the renewable energy source and thus compare the power obtained with the power calculated in the previous time in order to extract the maximum power and inject in the power grid. Now I'm going to describe the main simulation results. In order to validate the current source converter operating as shunt active power filter, the electric vehicle charging process and the interface with the renewable energy source, the simulation results consist of DC-link current regulation, compensation of current harmonics and low power factor in the power grid by the current source converter operating as shunt active power filter, electric vehicle charging along with harmonic compensation by the current source converter, and injection of power in the power grid from the renewable energy source where the current source converter is also operating as shunt active power filter. One of the rules of the current source converter is to control and maintain the current in the DC link for a reference current that, in this case, is 50 amperes. The DC link current regulation is made through the PI controller, and as it can be observed, the DC link current decreases. However, the DC link current quickly reaches the reference current. This happens when starts the electric vehicle charging. Here it is presented the simulation results of the power grid voltage and the power grid current before compensation. So, the current source converter is not operating as shunt active power filter. As it can be observed, the power grid current is not sinusoidal and in phase with the power grid voltage, and it presents a more harmonic distortion of 36%. After the DC link regulation, the current source converter operates as shunt active power filter, producing a compensation current in order to compensate the current harmonics and low power factor in the power grid. This figure shows the power grid voltage and power grid current after compensation, where the power grid current is almost sinusoidal and in phase with the power grid voltage. The harmonic distortion in the power grid current is reduced from 36% to almost 6%. In relation to the lithium battery charging and discharging process, this figure shows the grid-to-vehicle and vehicle-to-grid modes. During grid-to-vehicle operation mode, the electric vehicle is charged for a reference current of 10 amperes with a minimum voltage of 250 volts. The electric vehicle charging process consists of two charging stages, namely constant current followed by constant voltage. Initially, the electric vehicle is charged with a current of 10 amperes, whose power is supplied by the power grid and the renewable energy source. When the voltage in the electric vehicle reaches the maximum voltage of 450 volts, the electric vehicle current starts decreasing until it reaches approximately 0 amperes. During the vehicle-to-grid mode, the power from the electric vehicle is injected into the power grid for a reference current of 2 amperes, which corresponds to the electric vehicle charging stage. During all stages, the current source converter is controlled to operate as shunt active power filter. During the electric vehicle charging and injection of power in the power grid, it cannot be neglected the power quality improvement. So, the shunt active power filter continuing operating and the current harmonics in the power grid is compensated. In this figure is shown the power grid voltage and the power grid current after compensation during the electric vehicle charging process. The harmonic distortion of the power grid current is reduced from 6% to almost 3%. Finally, it is carried out the injection of power from the renewable energy source, where it is also made the compensation of the current harmonics in the power grid side. This figure presents the power grid voltage and the power grid current after compensation, where the power grid current is in phase with the power grid voltage, whose harmonic distortion value is 8%. This paper presents a single-phase current source converter with a hybrid converter to interface an electric vehicle and a renewable energy source. The current source converter can be controlled as shunt-active power filter for compensating current harmonics and low power factor, and also to allow the bidirectional operation for the electric vehicle and renewable energy source interface. Taking into consideration the preservation of the battery's lifetime, the constant current and constant voltage control was adopted. Regarding the renewable energy source interface, it was implemented a maximum power point tracking circuit in order to extract the maximum power and to inject in the power grid or charging the electric vehicle. The obtained results shows the correct operation of the current source converter operating as shunt active power filter, as well as operating in bidirectional mode to interface the electric vehicle and the renewable energy source. Thank you for your attention.
Hello everyone, thank you all very much for watching my presentation. Let me introduce myself. My name is Anna and I'm one of the responsible for a regression model to assess social acceptance of the demand response programs. My presentation is divided into 5 different parts. First, we'll address the motivation for this work, followed the objectives, then methodology applied in this work will be explained, and finally the results and conclusion will be presented. The demand response can be defined as a change in the electric usage by end-use consumers from their normal consumption patterns in response to change the price of electricity over the time, or to incentive payments designed to induce lower price use at the times of high wholesale market price, or when system reliability is jeopardized. As you can see in the figure, the demand response programs can be divided into different categories: price-based demand response, and this category includes the time of use tariff, critical peak price, and the real-time price. This category provides consumers time-varying rates that reproduce different value and cost of electricity throughout the day. Also, if the price varies significantly between hours or periods, the end users need to adjust the timing of consuming to get the benefits of the lower price. On the other hand, incentives-based demand response programs and this category comprise direct load control, interruptible curtailable service, demand bidding buyback, capacity market program, and ancillary service markets. And this category gives consumers load reduction incentives, and these load reduction are requested when the system is overloaded or when the electricity prices are very high. Now, Considering the domestic sector that represents a significant share of total electricity consumption, about 26% in 2015 in European countries and almost 28% for Portugal. So it is evident that development of solutions to mitigate energy use and manage electricity usage should be included in the domestic sector. In this way, the demand response could be an important tool by encouraging end users to shift the electricity usage for the demand periods when the electricity price is lower, which are also based on the higher share of renewable energy source, thus contributing to reduce the intermittence of renewables by reducing demand at times of low renewable supply and increasing the demand at times of surplus of renewable energy is available. Besides this, it is also expected a large-scale electrification of the transportation and heating sectors, and consequently is expected a significant impact on energy consumption. Though this has been creating a growing interest on the demand flexibility. Given this context, the end users' participation in the demand response programs could play an important role in the electricity system management. Now I'd like to look at the central aims of this research that intends to propose a methodology to assess the social awareness and acceptance of the demand response, which was based on extraordinary data. This methodology formulates different regression models to determine the most critical drivers to encourage domestic consumers' participation in the demand response programs and their level of acceptance. The data for this study was obtained from a questionnaire conducted by phone during May or June of 2018, and this questionnaire was administered to residents that were selected randomly from all Portuguese municipalities that covered both rural and urban areas. In total, 385 valid responses were considered in this study. Now addressing the questionnaire that comprised 4 different sections. The first section addressed the social demographic characteristics of the respondents. In the second section is about knowledge and dynamism of the respondents, which aims to assess knowledge of Portuguese on the electricity tariffs, asking them if they are familiar with the terms of bi-horário and tri-horário. To assess the dynamism of household was used as a proxy for 3 indicators: the regular communication of electricity usage to the electricity supplier, electricity switching supplier in the last 2 years, and the ownership of electricity monitoring device, for example a smart meter. The third section evaluated the motivational factors for energy management, which are the environmental factors, reducing the dependence on imported energy, reduction of electricity bill, and following advice from a friend or relative, among others. Finally, the flexibility electricity demand acts as a filter to understand the willingness of the Portuguese citizens to shift the start of a domestic appliance. For example, washings and dryer machines, against the potential cost saving. Also, a 5-linker scale was used to measure the agreement of the Portuguese respondents: totally disagree, tend to disagree, tend to agree, totally agree, and doesn't know, doesn't answer. After closing the questionnaire, the results demonstrate that the majority of the respondents are female. About education level, more than half of the respondents have a higher education level, about 40% have a degree, while about 25% of the respondents have studied less than 10 years in the school. Also, a large proportion of the respondents are aged between 25 and 64. Besides, the majority of them are part of the active population. Another relevant questionnaire results suggest that Portuguese citizens are familiar with time of use tariffs, and more than 84% of the respondents answer that they are familiar with the possibility of switching the flat tariff to time of use tariff. Also, the majority of the respondents are willing to defer their daily electricity consumption, encouraged by the proposal to benefit the environment, reduce the energy imports, or reduce the energy bill. On the other hand, follow advice from a friends, relatives, and neighbors, among others, while it was a knowledge, doesn't play a significant role in the decision maker of the respondents. As mentioned before, this study used an empirical research method to assess social awareness and acceptance of the demand response programs. In this presentation, we will be focused on the motivational factors to shift electricity usage. For this purpose, 4 different regressions were formulated. The first one used as a dependent variable environmental factor. Second, used as a dependent variable reduce energy imports. Third, use the reduction of electricity bill as a dependent variable. And last, use recommendation as a dependent variable. The explanatory variables used in this study are the gender, age, education level, professional activity, household size, living in a rural or urban areas, the knowledge on time of use tariff, the regular communication of electricity consumption to their electricity supplier switching during the last 2 years, and ownership of an electronic monitoring device, for example, the smart meter. I would also like to emphasize that all dependent variables used an ordered scale: totally disagree, tend to disagree, tend to agree, and totally agree. Now I'd like to move for the methodology, which was divided into different 5 stages. The first stage is focused on the classification of the dependent variables, as demonstrated in the above table. An ordinal response with a meaningful sequential order was used. As such, the order-logist regression or order-probit regression are the most suitable regressions to be applied. However, due to the simplicity and the direct interpretation of the results, was decided to choose the order-logist regression. After introducing the traditional order-logist model, it is required its validation, so it's needed to ensure the proportional parallel lines assumption. For this purpose, were conducted 2 different tests, the Brandt and Wolff-Golf. And according to the provided results of this both tests, the proportional parallel lines assumption was violated for almost dependent variables. The only exception was for the dependent variable recommendation, which the p-value is higher than 0.05, so the proportional parallel lines assumption was not violated. In the third stage, given the violation of the assumption for the order-logist model following the literature, the generalized order-logist model can fit the parallel lines assumption that is frequently violated by models fitted by the order logist model. However, when we compute the predictive probabilities, we face the problem of a negative probability. A possible explanation for this fact could be related to a high standard error on the response. For example, a large share of the respondents say that are totally agree to defer their electricity consumption motivated, for example, the economic compensation. And given these limitations, the heterogeneous choice model could be an interesting model to be applied since specify the determinants of the heteroscedasticity and attempt to correct it. This model also discloses how the choice and variance equations are combined to come up with the probability for any response. On the fourth stage was performed the Bayesian information criterion and archaic information criterion statistics. This statistic test aims to compare the relatively plausibility between two different models, the heterogeneous choice model and stereotype logistic regression, in order to find the best model to be applied. And according to the results of the both tests, the heterogeneous choice model was the most suitable to be applied. And the result of the fifth stage was used as common practice to estimate the model robustness by analyzing if coefficient change the effect, positive or negative, when the regression model is modified. The comparison between the three models was performed, and no significant difference was found on the estimated coefficients. The chosen model, in this case the heterogeneous choice model, could be considered robust, and the results can be interpreted as a true causal effect between explained variable and explanatory variables. This leads me to the next point, the results that were based on two different regression models, the heterogeneous choice model and the order logist model. As we can see in the table, concerning the environmental determinants, the equation choice results suggest that a large household and knowledge of the possibility to shift from a flat tariff to time of use tariffs influence positively the respondents to shift their electricity consumption motivated by the environmental benefits. On the other hand, in the variance equation, a positive coefficient suggests that respondents living in a large household and who own a smart meter tend to present more dispersed on variable attitude towers participating in demand response, while a negative coefficient indicates that the variability in attitude to environmental benefits decline across the value of the electricity bill, meaning that the respondents paying large bills will tend to present less variable response. Now, regarding to the economic determinants, women and the people who living in rural area are more likely to shift their electricity consumption, encouraged by the potential finance gains. A negative coefficient in the variance equation reveals that the variability of the response for old people and large households is lower than younger respondents living in the small households, while a positive coefficient in the variance equation suggests that the group of people who have a knowledge on time of use tariffs and who regularly communicate with the electricity supplier tend to present a more dispersed response about shifting the electricity usage motivated by the financial issues. Regarding the energy import, the female gender and familiarity on time of use tariffs, as well a large household, are significant factors for the choice equation, showing that this group tend to present more sensitive to the energy dependence argument to participate on the demand response programs. On the other hand, a positive coefficient in the variation equation suggests that the group of people who lives in rural areas and who regularly communicate with the electricity supplier tend to present more dispersed response concerning shifting the electricity usage motivated by imported energy reduction. And regarding follower recommendation from a friend or relatives among others, only a large household have a positive effect to shift the electricity usage. In conclusion, let me sum up the main points. The results suggest that the female gender consumers are more willing to shift electricity usage compared to the male gender. This could be explained by the fact that women are strongly associated with the household chores like a laundry and the use of domestic appliances, for example as washing machines and dryers, which have a higher potential to increase the demand flexibility. The results also indicate that the level of higher education could increase the source of the demand response, and this group could be also related to high use of new technologies, that it is the first step towards a wide implementation of the demand response. Also, the demand response program's implementation seems to be easily accepted by people living in urban areas, which can create interesting synergies with the emergence of smart and sustainable cities. Another relevant result found that flexibility is greatly linked to the cost determinant. It is particularly important that the potential cost savings can somehow compensate for the inconvenience which may arise from the increase in the flexibility, with impacts on the daily routines as well as in the comfort of the household. I would also like to highlight that the environmental concerns play an important role in the willingness to participate in the demand response programs, deployment and dissemination. Here we have the acknowledgement, and that brings me to the end of my presentation. Thank you very much for your attention.
Hello and welcome to the presentation of the paper Smart Charging and Renewable Grid Integration, a case study based on real data of the island of Porto Santo, created by Leo Strobel, Jonas Schlund, Veronika Brandmeier, Michael Schreiber and Marco Bruckner in a cooperation between the Mobility House and the Friedrich Alexander University of Erlangen-Nürnberg. First, let us begin with a quick overview over the content of this presentation. I will describe our motivation and the project of Porto Santo and the island of Porto Santo itself. Then this will be followed by our results in our data analysis and of our optimization, followed finally by a quick summary of our results and our insights. We were mainly motivated to create this case study because of the increasing numbers of electric vehicles that we will currently see across the globe, and here an example in the European Union. An increased amount of electric vehicles might come with certain challenges for distribution system operators, such as increased peak loads due to uncontrolled charging. However, if the charging might be undertaken smartly, electric vehicles can deliver significant flexibility to the electric system and therefore integrate better volatile renewable energy sources, and if they are provided with bidirectional charging, they might provide even additional storage capacities. Our contribution in this paper is that we give insights on the electric vehicle charging behavior based on real-world data where smart charging is already possible, meaning that the users are aware and can make themselves schedules so that a smart algorithm might dispatch their charging demand for their vehicle. This is already the case on the island of Porto Santo. We discussed these smart charging opportunities and how they lead to increased renewable integration and what potentials of renewable integration might be possible. And we study the flexibility of the smart charging, of this charging, and how it might behave over time. Now I will tell you something about the project of Porto Santo. And the project of Porto Santo was created by Renault and EEM, Madeira's electricity company, to make Porto Santo a smart and completely fossil-free island. Achieved through a combination of photovoltaics, wind, electric vehicles, and second life batteries. The Mobility House supported this project by developing smart charging and energy management system that optimize the interaction between the electric vehicles and stationary storages. In the first project phase, 20 electric vehicles were distributed on the island, of which 14 are Renault Zoes with 41 kWh battery capacity, and 6 are Renault Kangoos with 33 kWh battery capacity. These were distributed among public institutions such as the police, private companies like taxis, and private individuals. So that these vehicles might be charged as well, 33 charging stations were installed on the island. All of them were equipped with a controller and internet connection by the Mobility House so that smart charging is enabled. Some of these charging stations are only accessible to one individual user, and we will call these home charging stations from now on, and some are publicly available to all. This fleet was then expanded with 2 bidirectional electric vehicles and stations. Each of these stations have 11 kW of maximum charging rate. The other stations have only a charging rate of 7.4 kW. It has to also be added that charging in the project duration was completely free for the customers. The island of Porto Santo is located 43 kilometers northeast of Madeira, and its main economic area is tourism. The population of 5,000 people might increase up to 20,000 occupants that are only there for a short period of time in peak times. The electric power system and transportation on Porto Santo is dominated by diesel generation at the moment. 17%, however, in 2017 were generated renewably using a wind of 1.1 megawatt hours and PV systems of 2 megawatts. Sorry, not hours, just 1.1 megawatts. This island has an isolated electricity grid that is not connected to Madeira. The number of vehicles on the island are 1,000, making the 20 that were distributed during the project phase less than 10%. The energy demand of Porto Santo is about 33 gigawatt hours per year. Let us now come to the data analysis and the data that we were provided by. We were provided with 3 data sets. One, an aggregated data set that contained information about the entire electric vehicle fleet. This dataset contained data from February of 2019 to July of 2019 in 10-second resolution. And there was information about the current charging capability. This means the maximum charging rate of the entire vehicle fleet, as well as the amount of charge energy at any given time of the entire fleet. This dataset does not contain any information about individual vehicles, and therefore it was expanded by an individual dataset with detailed information about 700 charging events from May 2019 to August of 2019, with features such as the driver ID, vehicle ID, charging station ID, plug-in and plug-out time, and the amount of charged energy. Complemented is this dataset with the electricity generation of January 2018 to August of 2019. We began our data analysis by having a look at the plug-in times of the vehicles and how these developed over a course of a day. We can see here that in the home charging stations there's a significant lower amount of vehicles charged currently plugged in during the day in working hours, and more vehicles charged in overnight, maybe unsurprisingly. And what is surprisingly, at least to me, is that there is never more than 7 vehicles plugged in at one time. Given there's 20 vehicles, we can see that a lot of vehicles might be plugged in not every day, but rather rarely. In fact, on average, every vehicle is only charged every 3rd day. The difference between weekends and weekdays is not very significant, and it follows essentially the same curve, but with a slightly lower average in fact of 0.5 vehicles less at any given time. The public charging stations has no clear shape, and there's just on average 1 vehicle plugged in at any given time in the public charging station. If you look at the aggregated charging profiles of the fleet, we can see a certain clear peaks over the course of a day. So that this is understandable, I first have to explain what the different colors in these bar graphs mean. The blue color, the blue bars mean that the capability, as I already explained, meaning the maximum charging rate of the entire vehicle fleet. Whereas the yellow value bar means how much energy was charged by the fleet with the smart charging algorithm. The must red bars mean how much energy was charged in an immediate charging manner, because certain schedules had to be fulfilled. What I mean by schedule is every customer had the option to set certain departure times and departure state of charges for his vehicle that had to be fulfilled. Any flexibility, because these vehicles might be far enough in the future, this departure times, are far enough in the future, so that there is a lot of flexibility in how the energy necessary might be charged, is dispatched with a smart charging algorithm. This is the value we see in yellow here. And if it becomes, however, necessary to charge as fast as possible to reach the state of charge, then we charge with the must value. We can see here that there are clear must charging peaks between 3 and 7 a.m. and smaller peaks during the weekday shortly before 5 p.m. These peaks are explainable because the default schedule says that at these 2 time steps 80% of the state of charge of the vehicle has to be reached. We can see here that in the event that the vehicle was plugged in at such a time that we could not flexibly charge enough energy until this time, then we have to charge with maximum rate and create these peaks. A thing that might incentivize that is the reason for this problem, especially in the morning, is that Porto Santo, the renewable energy generation is mostly photovoltaics, and therefore during the night it is very difficult for a smart charging algorithm to integrate renewable energy. Therefore, charging is delayed until it is necessary to charge to fulfill the schedule, creating this peak in the morning. On the other hand, during the day, we can see that there is a lot more charged with value and a lot less with must, because there is significant renewable generation, and therefore we can charge more flexible and more useful. During the weekend, in general, the energy demand is lower, and therefore we have lower charged energies. And we can see that especially during the day, there's less energy that has to be charged, and sadly, therefore, also less energy that can be charged usefully, and more that has to be charged at the end of the night with the must value. In total, the capability of the entire fleet can reach values of up to 73 kilowatts. And on weekdays, we have a consumption of an average 100 kilowatt hours of the entire fleet, whereas on weekends it drops to 87 kilowatt hours. And we can also have a look at the user behavior with certain metrics and look how for every charging event in the individual data these metrics might change. For this, we have also introduced the definition of time flexibility, that in general means the difference between the plug-in duration and the time it would take to fully charge the vehicle at a maximum rate. We can see in these graphs for charged energy, plug-in duration, and time flexibility in charging events that on average the Zoes charge more in a given event than a Kangoo, and especially in public charging events a Zoe charges less. Interestingly, here for the time flexibility, the Zoe has a time flexibility on average of about 4 hours on a home event, but only of like 1 hour in a public event. For the Kangoos, we can see that there are always clear 2 certain peaks for plug-in duration and time flexibility. However, we have to keep in mind that there are only 6 Kangoos distributed, so these might reflect more the behavior of one individual person. The charging events, all in all, are more on home and in general than on public, and in general most people only frequented one or the other. So if they had a home charging station available, only some individuals additionally used any public charging. The user behavior can be further analyzed if you have a look at when and where the charging events took place. In this graphic, we can see the plug-in times and the plug-out times of all the charging events in the individual dataset, and some clear behaviors become visible. First of all, we can see that some users are predictable, like the blue user here, whereas some others, like the green one, behave very different to the other drivers. Additionally, we can see clear differences between intraday and overnight charging. As we can see here, there is one large cloud in the middle and to the top of this graphic, which means of charging events that started during the day and ended during the day. In these charging events, it becomes very clear that, first of all, they are all less, 84% of them are less than 5 hours long, and there is a clear correlation between energy consumption and charging duration. As we can see here, the bubble size indicates the charged energy of this event, and in general, with increased duration, this direction, we can see that the bubbles increase. In fact, there's a correlation coefficient between charging energy and duration of 0.6 in this time frame. So we can say for intraday events that they are mostly short and mostly their length is mostly determined by the amount of energy that is required. Therefore, they are less flexible and will be ended most likely once the necessary energy is delivered. For the second cloud, we can see here in the lower right and continuing in the lower left, we can see overnight charging events that start in the evening and end in the morning. We can see here very much higher predictability of when these charging events will end. All of these events, as we can see, end between 6 and 10 a.m. At the same time, the start is less clear. Also, we can see that here is no clear correlation between energy and duration. The bubble sizes here are essentially pretty randomly distributed across the cloud. These events overnight are therefore way more flexible than the intraday events and can be used for smart charging quite easily. One problem with this, however, is that on Porto Santo, as I already shortly alluded to, the renewable energy generation is mostly large on intraday because of photovoltaics and low in the night. In the night, in fact, the renewable energy share drops to about 4.2% in the time frame that we analyzed. And therefore, it is sadly the case that at the time frame where the most flexible charging is possible, at the same time, renewable generation is the lowest. If you compare the values of renewable generation in general of 15.1%, it's actually quite impressive that the current smart charging strategy achieves higher renewable integration than the average in a time frame that has lower renewable generation in total. The current charging strategy achieves 16.4% renewable generation inside the charged energy of the vehicles, compared to 15.1% renewable generation share in total and 4.2% in the night. Another problem that became visible in the data analysis was the overall development of flexibility. For this, we analyzed the flexibility in any given week for the aggregated data set, therefore for the entire fleet, because there is a longer time frame we had available to us than for the individual vehicles. This approximated flexibility we calculated by taking the entire duration of 1 week and subtract from it the entire energy charged in that week divided by the mean capacity of the fleet in this given week. We can see a clear downwards trend over the project duration. What has to be said here is that the electricity provider of Madeira and at the same time that of Porto Santo was in close communication with the customers during the project duration and explained to them the benefits of longer and more flexible charging events. Therefore, this might be explained. This graph might we can see maybe here how the enthusiasm of the customers slowly fades over the course of the project duration. This raises questions of if this trend really continues for longer, of good incentives that might lead to increased flexibility in the future. The other part of the data analysis we undertook was the potentials of renewable integration in total. For this reason, we created optimizations to look with the data set how much renewable integration is really possible. We created 3 different optimizations to achieve this. All of these optimizations had the same general mathematical structure. There we wanted to increase the renewable share in the charged energy, while at the same time charging the same energy over a given period and not exceeding the maximum charging rate. The 3 different optimization problems differed only in the dataset used and in the length of the optimization horizon. The first optimization, we looked at what is possible if this barrier that we have seen between night and day charging would not exist. Meaning that what if we could charge at any given point of a day and how much renewable integration would be possible. This was done on the aggregated data set, and we did it in a manner that for every day we optimized the energy individually. The second optimization we took is what is possible if this barrier is not broken? What if only intraday events can be optimized and overnight we can optimize, but not between the two? We cannot shift energy between the two. This optimization was done therefore in 12-hour intervals between 7 a.m. and 7 p.m. and 7 p.m. and 7 a.m. respectively, again on the aggregated data. Both of these optimizations do not acknowledge individual constraints of each vehicle, but the given constraints are only fulfilled for the entire fleet. To test if this leads to big errors, we have made a third optimization on the individual dataset. Of course, this can only be done for a shorter period of time, but can be done to validate our approach. And this is undertaken for every individual charging event. From the plug-in time to the plug-out time, we optimize only the energy that this given vehicle has charged in the time frame. And we look how much shifting inside of the charging events could improve the renewable integration. The results show that there's actually large potential still for the integration of renewable energy if the barrier between intraday and overnight events can be broken. We can see here that from our current point of 16.4 renewable energy inside of the charged energy, we can go up to 26.5%. However, in the case of optimization 2, where only overnight and intraday periods can be optimized individually of each other, this value only drops to 20.1%, still an increase of 33% to the current point. We can see in the average charging power over the course of a day how this increased renewable integration is achieved in each case. We can see clearly for optimization 1 that a lot of energy is shifted to the intraday time, and actually the capacity between 1 and 5 p.m. is used almost completely. For the optimization 2, we can see that there's large differences in the intraday period by optimizing the energy charged in the intraday period best. Additionally, what is harder to analyze is how the energy in the overnight period is optimized because of the volatile nature of wind energy. If you compare our results of both with the optimization 3, where we had the closest, which is closest to reality, we can see that optimization 3 actually very closely follows optimization 2. In fact, in the time period the optimization 3 data was available, both of these have approximately 18.2 renewable share in the charged energy. This further we can see further from this that the barrier between overnight and intraday events is actually the most important part that currently constrains our ability to increase the share of energy for the electric vehicles in a significant manner. Yet still we cannot forget that percentages of 20% are possible even if this barrier exists. All right, what have we found out? First, we found out interesting insights on the charging behavior for different user groups on the island of Porto Santo and how they will use opportunities for smart charging. And as well, we find out what opportunities smart charging might deliver for the integration of renewables into the grid. Our further future work, we will investigate more data on the island of Porto Santo once the project is finished. And as well, we would like to implement an energy system model for studying the energy system of Porto Santo in general and what smart grid as well as smart charging strategies might enable us to do. Thank you very much. And do you have any questions?
Hello and welcome to my presentation. My topic is optimized power system voltage measurements considering power system harmonic effects. My name is Emeka Obikwelu. I am a PhD candidate at the Georgia Institute of Technology in Atlanta, Georgia, United States. I am also a registered professional engineer. And I am grateful for the opportunity to share my work with you today. Here's the outline I will use to cover my presentation, beginning with the background, providing the problem statement and scope of work, and then continuing through until the conclusion. The purpose of this presentation is to show you a new method for correcting for errors in power system voltage transformers using dynamic state estimation. I will focus on the case where the objective is to estimate a power system voltage signal that is corrupt or corrupted with harmonics. Harmonic distortion is a generalized term for describing the distortion of the power system voltage or current waveform by harmonics. Harmonics are the distorting signal components with frequencies that differ from the fundamental power system frequency by integer multiples. Now, regardless of the harmonic composition of the power system voltage, it must first be reliably captured before it can be usable in any secondary functions. And so this is where the voltage transformer comes in. In my work, it is both practical and beneficial to mentally frame the voltage transformation mechanism as a delivery system of sorts, one by which the reproduced power system voltage is delivered to the connected loads. This frame is how the concept of the instrumentation channel comes about. Now, beginning with the VT, the magnetic core of the VT, and ending at the load, the instrumentation channel is ideally intended to deliver a scaled-down replica of the power system voltage to the connected loads. The detailed electrical circuit model or equivalent of the voltage transformer instrumentation channel is provided next. In this diagram, you can see the different parameters that make up the detailed voltage transformer circuit model. You also see the other components of the instrumentation channel, that is, the cables and the connected loads. We will return to this figure on a later slide, but it is important to note that the dynamics of the parameters of the channel may impose limitations on its performance, that is, when the VT is energized. These limitations manifest as different kinds of errors. Therefore, voltage transformer manufacturers design VTs with accuracy ratings. And so when a VT is applied in a way that is consistent with its accuracy rating, any featured errors in its output stay within empirically predetermined and acceptable boundaries of error. The waveform distortion errors are quite interesting, and this is because they consist of both magnitude errors and phase angle errors. And so let me focus your attention on the harmonic distortion errors. But do take notice of two characteristics of the magnitude spectrum of the VT. And this is in the top plot on the right-hand side of the slide. First of all, you should notice that it behaves like a low-pass filter for higher order harmonics. Secondly, you should notice a spike, or sometimes it could be a dip, indicating a resonance effect. Harmonic distortion errors are generated generally in two ways. Number one, a power system harmonic coinciding with a natural frequency of the voltage transformer instrumentation channel. Taking note that there may be multiple natural frequencies of the channel, and this will tend to cause resonance and resonance effects like what I showed you in the previous slide. Number two, higher order harmonics being attenuated by the channel. Thus, the harmonic composition of the channel output voltage differs from that of the power system voltage. Now, we need to remember that the functional purpose of the voltage transformer is to reproduce the power system voltage as accurately as is required by its application. Therefore, it is important to develop methods for addressing these error possibilities. To this end, I will be discussing an error correction method that is based on dynamic state estimation. And so the core research problem statement reads as follows. Given discretized measurements of the output of the voltage transformer instrumentation channel with a known mathematical model, accurately estimate the VT primary voltage. The scope of presented work is essentially addressing this research problem in the case where the primary voltage is corrupted with harmonic effects. The first step in the methodology is the creation of the detailed electrical circuit model of the VT instrumentation channel. This circuit model is a high-frequency model that includes the parasitic or stray capacitances. Before identifying the state variables, some practical simplifications can be made for the purposes of this study. The simplifications are stated as follows. Number one, assume negligible excitation current. And so this removes the excitation branch from the mathematical model associated with the circuit model. Number two, neglect the stray capacitance effects, which is safe for this study considering the range of harmonics to be studied. After applying the above simplifications, the state vector can now be identified. Now recall that the state vector contains the least number of variables that can be applied to fully describe the circuit model. For the revised circuit diagram, there are thus 11 state variables, and this can be seen in the vector that is shown at the bottom of the slide. The second step is to develop the mathematical model for the circuit model of the VT instrumentation channel. Now, the mathematical model is a system of equations that theoretically describes the circuit model, where the equations are essentially functions of the identified internal state variables. There are 11 equations and 11 state variables associated with this model. And the equations comprise essentially nonlinear algebraic differential equations. In the third step, any nonlinear equation in the mathematical model with an order greater than 2 is quadratized. After quadratization, every equation in the model is at most of the quadratic degree, so an order of 2 or less. The process of quadratization introduces new state variables and an equal number of equations to the mathematical system model. And so you can see this on the slide here, the new state vector as well as the system model. When quadratization is needed and applied, the new model is called the quadratized dynamic model. On the slide, you can see again in the system model. Let me pull up the pointer here. This represents this is the matrix representation of the quadratic terms resultant from the quadratization process, and up here we have the new state vector comprising the previous state vector and the vector of the vector that comprises the terms that are added due to the quadratization process. In the fourth step, the measurement model framework is developed. The measurement model mathematically relates the measurements with the theoretical system model that describes these measurements in terms of the internal state variables. The error vector is included in the formulation to account for any mismatch or residual, and it sets up the framework for the optimization or for the development of the optimization problem or the objective statement in the optimization problem. And we'll get there in a few slides. In the fifth step of the methodology, the system model used in the measurement model framework is integrated using a novel numerical integration method called the quadratic integration method. The paper discussing this method is included in the references slide. Using the numerical time step h, the model is integrated twice as indicated in the slide. Therefore, the final model has twice the number of entries as the dynamic measurement model, and the final state vector has twice the number of states as the state vector of the previous measurement model or the dynamic measurement model. Two key notes or goals are tied to the use of the quadratic integration method. Number one, the system model equations are integrated assuming that the internal state vectors vary quadratically within each time step. Number two, the system model is reformulated as a fully equivalent system of, at most, quadratic equations or quadratic algebraic equations, excluding or with no differential equations. So if you take a look at on the right side of the screen, this is the matrix representation of the system model for the application of the method in the case of the current transformer. Here you see, let me use the pointer. So here's the system model that is used in the measurement model framework. This is the coefficient matrix associated with the linear terms or linear part of the model. This here represents the quadratic terms. This represents the coefficient matrix associated with the solution vector from the previous time step. And here, this represents the vector for or containing any constant terms. This vector right here is updated whenever the algorithm iterates or operates on a new sample. And you will see this in the explanation of the process flow of the algorithm. In the final methodology steps, the estimation problem statement is formed, that is, to solve for the best estimate state vector solution in a least square sense that minimizes the presented objective function. The solution method used is the Gauss-Newton iterative solution method. Finally, in step 8, the confidence level for each least square solution estimate is computed to quantify the match between the measurements and the model at the obtained solution estimates. So this concludes at a high level the description of the methodology. Now, here are some important points about the algorithm built on top of this methodology. Number 1, the algorithm is built on steps 7 and 8. And so, number 2, the processes in the previous steps, namely quadratization and quadratic integration, are not part of the execution timeline. Number 3, the previous steps are presented because they show how the essential matrices and vectors, which are unique to any given voltage transformer instrumentation channel, how these vectors and matrices are developed. And then these matrices don't change unless the VT and or the cables or the load are changed. Therefore, once developed, these vectors and matrices serve as inputs for the algorithm. On this slide, I show the process flow for the execution of the algorithm. It starts with capturing the first sample, developing the measurement vector from the streaming data, and then we go to, let me use the pointer here, and then we go to a pre-step to the iterative process where we formulate the Jacobian matrix and other vectors that are essential for the application of the solution method. Now, this block is really just shown for illustrative purposes because the Jacobian matrix can be developed or formed outside of this loop and used as an input into the algorithm, and so this cuts on saves on time. So again, this block here is really shown for illustrative purposes as a prelude to what comes next, which is the computation of the gradient. Now, if this value, following this blue line, is greater than a predetermined error margin, which is typically 1 times 10 to the negative 6, or to get to the negative 12, at the minimum 10 to the negative 6, then the iteration counter is incremented and the process is repeated until we have a gradient that falls lower than this error margin, in which case we proceed to computing the residuals, which now leads to the computation of the confidence level, and then we update the coefficient matrix associated with the solution vector from the previous step. And then we move on to capture the next sample and begin the process all over again. And so because the algorithm is designed to operate on a sample-by-sample basis, it is classified as being designed for real-time implementation. Other methods that aim to achieve the same purposes, some of them are designed to capture a certain number of samples, for example, half a cycle of samples first before they begin to produce their estimates. And so those methods are not real-time because by half a sample, you are half a sample late. By half a cycle, you are half a cycle late. But this method here operates on a sample-by-sample basis, and so it is classified as being designed for real-time implementation. And so I use the following methods to quantify and assess errors in the time domain. The provided formulas are used to compute the following types of errors: the error between the simulated actual primary voltage and the estimated primary voltage, and then the error between the simulated actual primary voltage and the secondary voltage, load voltage, scaled or referred to the primary side. So this essentially represents the uncorrected signal. And then the errors are compared. The first equation plots the instantaneous error. The second equation computes the error over the full simulation length. And that's the normalized root mean square error and RMSE in percent. The second error method is conducted in the frequency domain. Here I'm essentially zooming in to assess the error on a harmonic by harmonic basis by means of evaluating the harmonic energy spectrum. And so essentially I'm computing the error signal and finding the energy in the error signal, and using this energy or this error signal energy as the basis for comparing the output of the estimator and the output of the instrumentation channel in terms of how they differ from the actual voltage, power system voltage. So here is the simulation setup summary. The 9th and 11th harmonic signals are superimposed on the 60 Hz power system voltage with a total harmonic distortion level of 18%. The simulation duration is 500 milliseconds. The sampling rate is 80 samples per cycle, which translates to a sampling period or time interval of 208.33 microseconds. There are three use cases developed. In each of these cases, the load remains at 50 ohms, and the cable length is varied from 52.8 feet to 422.4 feet, and then to 844.8 feet. This variation in the cable length introduces errors in the channel for the purposes of this study. So here I begin the presentation of results. The first set of results are for use case 3, which is the case where the cable length is 844.8 feet. On this slide, I show the time domain as well as the phasor domain analysis results. The figure on the left, figure 6, shows the actual, estimated, and referred load voltage, that is, referred to the primary side. Figure 7, the figure on the right, shows the RMS of the signals in the top plot and their respective phase angles in the bottom plot. You can see in figure 7 that the estimator provides a more accurate output than the channel output. And so if I were to set up the pointer here, you see that the blue line here is the RMS associated with the ratio voltage. The dotted line is the RMS associated with the estimated voltage referred to the secondary side. And down here you have the RMS signal or plot associated with the VT load voltage. And you can see that the estimated voltage has an RMS plot or value that is much closer to the actual RMS values than the RMS of the load voltage. You see the same result in the determination of the phase angles. The phase angle plot associated with the estimated voltages, the dotted lines here, the dotted plot, And the blue line here represents the phase angles associated with the ratio voltage. And down here we have the phase angles associated with the VT load voltage. And again, you can see that the estimator provides a more accurate computation, a more accurate value for the phase angles than the phase angles computed from the output of the channel. For use case 3 as well, the error assessment is conducted in the harmonic spectral domain, as discussed earlier. This domain shows the spectral distribution of the error signal energy across the harmonics. The top plot of figure 8 on the left shows the spectral distribution of the error signal energy from comparing the actual voltage and the estimated voltage. The bottom plot of figure 8 on the left shows the spectral distribution of the error signal energy from comparing the actual voltage and the primary side referred load voltage. The results clearly show that there is significantly more error signal energy in the bottom plot than in the top plot. Thus, at the fundamental frequency, at the fundamental frequency, as well as at the 9th and harmonic and 11th harmonics. The spectral error signal energy distribution for the estimator output is so low that one must zoom in at the 4,000th level, that is 1 over 4,000, to see anything. And you can see this in the top plot of figure 9 on the right. The bottom plot is unchanged for comparison, but the top plot on this figure here shows, again, noting the zoom in, the differences. Figures 10, 11, and 12 show the results for all three cases. Across all three cases, the results show that the estimator reduces the magnitude error by 85% to about 87%, and reduces the phase angle error by about 96% to just over 97%. And these are those percent error reduction values for the phase, for the magnitude as well as the phase angle error. Here in figure 12, assessing the error signal energy across all three cases, the results show that the estimator reduces the error signal energy by about 78% to just over 97%. Again, this is the column showing those values, and you see the reduction produced by the algorithm versus the before correction values. And so, in conclusion, I have presented a new method for voltage transformer instrumentation channel error correction based on dynamic state estimation. More specifically, the method estimated with high accuracy the simulated power system voltage, which was distorted by multiple harmonics. The presented algorithm is designed for real-time implementation and shows promise as an innovative way to provide optimized power system voltage measurements. Thank you for your attention. I would be very happy to take your questions now.
Hello to everyone. I hope everything is fine with you, family and friends. I would like to greet the Organizing Committee and congratulate online approach, safeguarding the health of each one. Regarding the presentation, my name is Luis Barros and I'm here to present a paper with the title Submodule Topologies and PLM techniques applied in modular multi-level converters, review and analysis. The paper was developed by me and my colleagues Dr. Mohamed Tanta, Professor Dr. António Pina Martins, Professor Dr. João Luís Afonso, and Professor Dr. Gabriel Pinto. The structure of the presentation is very similar to that of the paper, presenting a comparative analysis of different power converters, topologies, that can be integrated into a modular and multi-level solutions. In the following topic, different PLM techniques for MMC application are analyzed. Electronics power converters have been used in many different applications. However, for very high voltage applications, conventional topologies are no longer viable due to the maximum operation voltage of the semiconductors. For this reason, it's necessary to migrate to a modular and multi-level solution. In this way, it is possible to obtain DC buses with lower voltage, reducing the voltage stress in the semiconductors. Additionally, the higher the voltage levels that the converter can synthesize, the smaller the harmonic spectrum of the output voltage. With this, it is possible to integrate smaller passive filters, providing more compact and more efficient solutions. That said, the next big question is, what type of power converters topologies can be integrated into each submodule of MMC? So, different topologies were analyzed from the point of view of the output voltage, being the DC bus dimension taking into account this requirement. Power converter topologies like the half bridge with a split DC bus, the conventional half bridge submodule, the full bridge, the NPC, the tie-NPC, and the fly capacitor multi-level converter. Comparing all the power converters topologies, considering the number of semiconductors, the complexity of the topology, and other features, was possible to conclude that the full bridge topologies seems to be the most interesting solution to be integrated into MMC application. Once the topology is defined, it becomes necessary to implement PLM techniques to control the MMC submodules. Once again, a comparative analysis of different PLM techniques is presented based on computer simulation, taking into account submodules consisting of full bridge. Regarding the PLM techniques, three groups can be highlighted: the level shift carrier, the phase shift carrier, and the hybrid carrier. Initial focus only on the level shift PLM technique. There are the phase disposition, the phase opposition disposition, and the alternate phase opposition disposition. The carrier waveforms have the same amplitude and frequency, but are arranged vertical with different offset values. The carrier waveforms of the phase disposition PLM technique have the same phase angle. The carrier waveforms of the phase opposition disposition PLM technique have a symmetry in relation to the zero reference line, with the carrier waveforms lower than this value in phase with each other, but 180 degrees out of phase in relation to the upper carrier waveforms. The carrier waveforms of the alternate phase opposition disposition technique are alternately 180 degrees out of phase. Since the carrier waveforms have a symmetry in relation to the zero reference line to the x-axis, the synthesized output waveform also has a symmetry. To note that the level shift PLM techniques were initially proposed for the control of MMC based on topologies such as the NPC or the fly capacitor. Note that are topologies with more than two semiconductors in series. And when these modulation techniques were implemented in MMC solutions consisting of full bridge submodules, it causes power imbalance in the different submodules. So, to mitigate these imbalance power problems, a carrier permutation technique is necessary. With the permutation of the carrier's waveforms, it is possible to obtain a more symmetrical output waveform. Another variant of level shift modulation technique consisting of overlapping the carrier waveform that will create a greater number of intersections between the modulating waveform and the carrier's waveforms. Likewise, it is possible to vary the frequencies of the carrier's waveforms when the output current reaches to the peak values. The voltage of the capacitors in the peripheral submodules tends to oscillate, and in order to mitigate this phenomenon, a higher frequency in the top and in the bottom carrier waveforms was considered. With the increase of the frequency in the peripheral submodules, it is possible to decrease the voltage ripple of the existing waveform in the DC link capacitors and consequently improve the quality of the output waveform. In turn, another variant of this control, the variable frequency 2, was initially created in order to equalize the losses along the NPC topology. Since the IGBT device positioned on the periphery of the converter switch at higher frequency, the frequency of the intermediate carrier waveforms was increased in order to equalize the transitions. Here is possible to see that none of the PLM techniques is able to synthesize a symmetrical output waveform. Regarding the phase shift carrier technique, how the carrier's waveform share the same amplitude, the same frequency and offset value, varying the phase angle between them. This modulation technique provides a greater balance in terms of power of the different submodules. In fact, is what is pretended in a modular application. Nevertheless, the phase shift carrier PLM technique is easier to implement in a digital signal control once already exist registers to implement the phase shift of the carrier waveforms. Here is possible to see that this PLM techniques is capable to synthesize a symmetric output waveform. The hybrid modulation methods take advantage of the best feature of the previous techniques. The phase shift disposition technique arises from the combination of the phase shift carrier with the phase disposition. Looking at the carrier's waveforms, is possible to see and to identify an equal group of carriers above and below the zero reference value. Additionally, is possible to see that the carriers show a symmetry that will reflect in a symmetrical output waveform. If we combine the carrier overlapping with the phase disposition, the carrier overlapping with the phase opposition disposition, and the carrier overlap with the alternate phase opposition disposition, is possible to obtain the remaining combination for the hybrid carrier PLM technique. Here is possible to see that only these two techniques are capable to synthesize a symmetrical output waveform. Analyzing the THD value of the PLM techniques, is possible to verify that the phase shift carrier and the phase disposition techniques presents the lowest value. With this paper was possible to conclude that different PLMs convergence topology was studied, highlighting the best solution to be integrated into MMC. Different PLM techniques was analyzed and compared, highlighting the technique with the lower THD value. For the present case study, can be concluded the PLM techniques with carrier are symmetrical to x-axis to the zero reference line, allows to a symmetrical output waveform. Overlapping the carrier waveforms results in a great number of intersections. The phase shift carrier and the phase shift dispositions allows to synthesize a output waveform with low THD value, and the phase shift carrier is more simple to implement in a digital signal control. Thank you very much for your attention.
Hello everyone, my name is Tiago Souza and I'm a PhD student at the group of Power Electronics and Energy of University of Minho, Portugal. I'm going to present a paper named Battery Charging Station for Electric Vehicles based on bipolar DC power grid with grid-to-vehicle, vehicle-to-grid and vehicle-to-vehicle operation modes. So, it is known that electric vehicles are a promising alternative to the conventional vehicles based on internal combustion engines regarding the emission lessening of greenhouse gases and exploitation of fossil resources at the user level. Furthermore, in addition to the advantages in terms of mobility, electric vehicles are also a promising solution concerning smart grids, since they can provide ancillary services in conjunction with renewable energy sources and energy storage systems. However, to make electric vehicles ascend to a global level, a suitable infrastructure in terms of battery charging is mandatory. In this sense, several scheduling strategies regarding EV battery charging stations have been proposed in the literature, as well as battery swapping strategies, and also the combination with energy storage systems and solar photovoltaic panels. In addition to electric vehicles, DC power grids have also been gaining attention. mainly due to the fact that energy storage systems and solar photovoltaic panels, which are major assets towards distributed generation and consequently smart grids and microgrids, operate in DC. Moreover, DC power systems are more efficient than their AC counterparts, since they do not suffer from skin effect and they don't present electrical issues such as reactive power and harmonic currents. In this sense, DC microgrids have also been an important research topic. A DC microgrid can be either unipolar or bipolar, depending on the number of active conductors, which means excluding the neutral wire. As suggested by their designation, bipolar DC power grids provide two symmetrical voltages referenced to the same potential, which is a neutral wire. Additionally, it is possible to obtain a voltage that is the double of the base value, namely by using the negative rail as reference instead of the neutral wire. This is advantageous in the way that allows to have two different voltage values instead of only one, as happens with unipolar DC power grids. Besides, bipolar DC power grids are more reliable and present a higher energy transmission capacity. The application of bipolar DC power grids in electric vehicle battery charging stations is not a novelty. In the literature can be found an electric vehicle battery charging station based on a neutral point clamped front-end AC-DC converter, whose split DC link generates a bipolar DC power grid, where the DC-DC converters responsible for the battery charging operation are connected to. However, only the front-end AC-DC converter is addressed in such work. Some proposals study the utilization of three-level DC-DC converters in an electric vehicle battery charging station based on a bipolar DC power grid, but the vehicle-to-grid operation mode is not addressed. So, taking in consideration the aforementioned drawbacks found in the literature, this paper presents an electric vehicle battery charging station based on a bipolar DC power grid with vehicle-to-grid capability, besides the obvious grid-to-vehicle functionality that is a primordial goal of a battery charging station. Besides, the vehicle-to-vehicle operation mode is also taken into consideration, which is a relatively recent operation mode regarding electric vehicles, but being already a relevant research topic since the past 2 years. It should be noted that the front-end AC-DC converter of the electric vehicle battery charging station is not addressed in this paper. This figure shows the structure of the electric vehicle battery charging station, where it can be seen that the chosen topology for the DC-DC converter is the 3-level 2-quadrant buck boost, since it is bidirectional, which allows bidirectional power flow and hence the grid-to-vehicle and vehicle-to-grid operation modes, among others, and also because it has a split DC link in its high voltage side, which makes it suitable for bipolar DC power grids. Other advantages of the 3-level 2-quadrant buck-boost DC-DC converter include the reduction of semiconductor voltage stress due to its multi-level characteristic and lower ripple in the inductor current. The figure of the structure suggests the modularity of the electric vehicle battery charging station, being possible to connect an indefinite number of similar DC-DC converters to the bipolar DC power grid. But for the sake of simplicity, the analysis carried out in this paper only comprises 2 DC-DC converters, which represents 2 electric vehicles. Each converter X, with X varying from 1 to the total number of converters, in this case being 2, is connected to an EVX in the low voltage side through an inductor LX, and to the bipolar DC power grid in the high voltage side, with each DC link capacitor being connected in parallel to each of the rail voltages of the bipolar DC power grid. Since the DC power grid voltages are symmetrical, as is supposed in the bipolar DC power grid, the total voltage in the high voltage side of each converter is 2 VDC pos, which means the double of the positive rail voltage. However, due to the 3-level characteristic of the converter, each power semiconductor withstands only a maximum voltage of VDC pos, which means the positive rail voltage of the bipolar DC power grid, or in other words, half the total DC link voltage. Similarly to a traditional 2-level buck-boost DC-DC converter, the operation of this converter can be divided into main operation modes, namely the buck mode and the boost mode. In the buck mode, power is transferred from the high voltage side, which means the DC power grid, to the low voltage side, which is the battery. This operation corresponds to the G2V operation mode. In the figure are highlighted the power semiconductors in operation during the buck mode. These equations show the states that each converter X can assume, as well as the voltage level produced for each state. State 0 means the switch is open, and state 1 means the switch is closed. It can be seen that when both switches are turned off, the voltage produced by the converter is 0. When both switches are turned on, the voltage produced by the converter is 2 VDC pos, which means the total DC power grid voltage. And there is an intermediate state which can be produced by turning one of the switches on and the other off, which means it can be done in 2 ways. And the voltage level produced in this case is VDC pos, or in other words, half the DC link voltage. And it should be referred that the switching signals of the 2 power semiconductors of the same converter must be 180 degrees phase shifted in order to assure the proper operation of the converter. This 180 degrees phase shift also doubles the frequency of the voltage produced by the converter with respect to its switching frequency, which will also increase the frequency in the inductor current. Besides the multiplication effect in the ripple frequency, the 180 degrees phase shift makes it also possible to have zero ripple in the inductor current when the duty cycle is 50%, since the voltage produced by the converter is constant in this situation. This zero ripple also happens at 0% and 100% duty cycles, as happens in a traditional 2-level buck-boost DC-DC converter. In order to control each EV battery current, a predictive control strategy was employed based on the model of the converter. This equation shows the voltage that each converter X must produce in a given instant K in order to control the EV battery current IBAT X according to its reference, IBAT ref X, for the buck mode, which means when IBAT is higher than 0. Lx is the inductance value of the inductor of the converter, and Fs is the sampling frequency of the control system. Regarding the boost operation mode, power is transferred from the low voltage side, which is the battery, to the high voltage side, which is the DC power grid. This operation mode corresponds to the V2G. In the figure are highlighted the power semiconductors in operation during the boost mode. These equations show the states that each converter X can assume, as well as the voltage level produced for each state. Contrarily to the buck operation mode, when the two switches are closed, level 1, the produced voltage is 0. When both are opened, level 0, the voltage produced is 2 VDC pos, and in the same way as the buck mode, the combinations to produce the intermediate voltage level VDC pos is to have one switch closed and the other one open. And as presented for the buck mode, the 180 degrees phase shift must also be applied. This is the predictive control equation for controlling the battery current in boost mode, which is very similar to the one previously shown for the buck mode, basically differing only in the signs of the current. In this case, this equation is only valid for IBAT values lower than 0. Moving forward to the computational simulations, those were carried out in the software PSIM 9.1 from PowerSim. Here are presented the parameters of the power converter and batteries of each electric vehicle, where it can be seen that the converters are equal, as well as the batteries, only presenting different initial voltage values, with VBAT 1 starting with 250 volts and VBAT 2 with 200 volts. Both the switching frequency of the semiconductors and the sampling frequency of the control system were chosen to be 50 kHz, but as it will be seen afterwards, the arrangement of the converter allows to have a produced voltage of 100 kHz. The used model for the battery is a second order model, namely the Tevna battery model, which contains a resistance in series RSX, which means the shunt resistance, the internal resistance of the batteries, parallel resistance, which is RPX, which emulates the self-discharge of the battery, and CBAT-X, which is a capacitor that emulates the dynamic behavior of the battery. Besides, there is also a voltage source VOCX, which means the open circuit voltage of the battery. This module was considered enough to emulate the charging and discharging processes to validate the operation of the charging station. Now, going to the simulation results. Here can be seen the traditional charging operation, grid to vehicle, with both EVs charging with the same current of 20 amps. These waveforms show the voltage and current of both batteries, the currents absorbed from the DC power grid, and the voltages produced by each converter. The battery current waveforms are not identical due to the difference in the battery voltages, which results in different duty cycles applied to the converters. In the case of converter 2, because its battery voltage is practically half the total DC power grid voltage, around 200 volts, its duty cycle is around 50%, which makes the respective produced battery current to have a negligible ripple. Here can also be seen the frequency multiplication effect in the produced voltages and consequently in the battery currents, since only 2 switching periods are presented, but these variables present 4 periods, each with a frequency of 100 kHz. Regarding the 3 grid currents, it can be seen that the positive rail current in red and negative rail current in blue are symmetrical, and thus the neutral current in green has a null average value, which means that the bipolar DC power grid is operating in a balanced way. Here it can be seen the same result as the previous one, but with EV2 charging its batteries with a higher current value, namely 40 amps. This result aims to simulate a case of unbalance to the grid, but it can be seen that the positive and negative rail currents are still symmetrical, and the neutral current has no DC value. Thus, the charging station is able to consume balanced currents from the bipolar DC power grid, even with unbalanced battery charging operation. Here is presented the vehicle-to-grid operation mode, with both EVs providing the same current to the bipolar DC power grid. In this case, the battery currents are negative, meaning that the electric vehicles are acting as power sources instead of loads, and for this reason the currents in the power grid are inverted, which is the positive rail current presents negative values and vice versa. Nevertheless, the neutral current has no DC value, meaning that the power is being injected to the bipolar DC power grid in balanced conditions. In this result, it can also be seen that due to the internal resistance of the batteries, because both vehicles are discharging, its battery voltage drops, and in the case of VBAT2, its value drops below 200 volts, which is half the total DC link voltage of the DC power grid. Due to this, the voltage levels produced by the converter 2 are 0 and 200 volts instead of 200 and 400 volts like the previous case, and such as the other converter. Here is presented a similar result as the previous one, vehicle to grid, but in an unbalanced way, with EV1 discharging its batteries with 20 amps, but EV2 doing the same operation with 40 amps. Once again, the grid currents are symmetrical, and the neutral current has no average value, proving that the charging station can provide balanced currents to the bipolar DC power grid, even with unbalanced discharging from the electric vehicles. Here is presented the vehicle-to-vehicle operation mode, where a vehicle provides power to another without using the power grid. In this case, EV2 is charging with 20 amps, and EV1 provides the necessary current to the other EV. Differently from the other results, in this case all the grid currents present 0 DC value, meaning that the bipolar DC power grid is neither providing nor absorbing power. Hence, this result shows that the charging station is able to exchange power among the electric vehicles without using the front-end AC-DC converter. Here is presented a combination of vehicle-to-vehicle and grid-to-vehicle, which means that EV1 provides power to EV2, but this power is not enough to perform the charging with the desired value. So a parcel of power must be provided by the bipolar DC power grid. In this case, EV2 is charging with 40 amps and EV1 is discharging with 20 amps. Once again, it can be seen that the grid currents are symmetrical, but their average value is low in this case due to the contribution of EV1, which means that the bipolar DC power grid only provides the power difference between the power required by EV2 and the power supplied by EV1. Here is presented a combination of vehicle-to-vehicle and vehicle-to-grid, which means that EV1 provides power to EV2, but this power is more than enough to perform the charging with the value desired by EV2. So a parcel of this excess power is absorbed by the bipolar DC power grid. In this case, EV2 is charging with 20 amps and EV1 is discharging with 40 amps. The grid currents are once again symmetrical and inverted, meaning that the grid is receiving power and this power corresponds to the power difference between the power supplied by EV1 and the power required by EV2, as mentioned before. Here can be seen an overview of the 7 simulated cases for the electric vehicle battery charging station, where are presented the average values of the main currents involved, namely the 2 battery currents and the DC grid positive rail current. The negative rail current is not presented because its average value is always symmetrical to the positive rail current, and the neutral current is not presented because its average value is always 0, as expected. It can be seen that all the cases emulate all the conditions that can be verified in a grid, either concerning the power direction, with G2V and V2G, either concerning balanced and unbalanced operations. So, for concluding the paper, it was presented a charging station for electric vehicles based on a bipolar DC power grid, which uses 3-level bidirectional DC-DC converters. Only 2 electric vehicles were considered, but the charging station is modular, which can be extended to an indefinite number of vehicles. Based on computational simulations, the operation modes grid to vehicle, vehicle to grid, vehicle to vehicle, and combinations of vehicle to vehicle with the first 2 were verified, both with balanced and unbalanced conditions. In all cases, it was verified that the charging station is able to provide or absorb balanced currents even with unbalanced operation from the electric vehicles. I hereby finish my presentation. Thank you for your attention.
Good afternoon to everyone. My name is Vitor Monteiro and I'm here on behalf of Professor João Luís Afonso, General Chair, and Professor Gabriel Pinto, the General Co-Chair. This is the closing session. It was a pleasure for us to receive you on this virtual conference. thank you very much for the questions, for the authors, and thank you the authors for the answers. Moving forward to the best paper award, it will be announced right now, and the best paper is battery charging station for electric vehicles based on bipolar DC power grid with grid to vehicle, vehicle to grid, and vehicle to vehicle operation modes. And the first author of this paper is Tiago Souza from University of Minho. This is an information about the process based on the 4 reviewers of this paper. It received a score of 4.75 on the maximum scale of 5. And just for information, the paper with the lowest score was accepted with 3.25. Congratulations, Tiago Souza. I don't know if you are here, but congratulations for this achievement. Tiago and all the authors of this paper, of course. So, before closing the conference, we would like to show you some photos about our university. If you intend to visit us, not now but in the future, you are more than welcome. The University of Minho is comprised of 2 campi. This is the Gualtar campus in the city of Braga, and the Azurém campus in the city of Guimarães. Both cities are very beautiful. The university is divided in these two cities, and both cities are very beautiful to visit. And if you intend to visit us, you are more than welcome. So, regarding our research group, we would like to highlight our main areas of actuation, of research, regarding power quality, electric mobility, industrial applications, railway systems, wireless power transfer, and renewable energies. We have more specific areas, but this is the main 6 areas of research that we have in our research group, the group of power electronics and energy. We have a total of 8 PhD researchers, 5 PhD students, 11 MSc researchers, and 15 students finalizing the master dissertations. So, thank you very much for your participation in this virtual conference. If you have any doubt, please don't hesitate to contact us. The papers will be indexed in the Scopus, and if you have more information, we'll provide to all the authors. So, finalizing, thank you very much.